Welcome back, everyone. I'm Ted Lang, and we are going to go into session 5 here of our meeting. Our first talk is going to be from Arshpreet Bassi on the application of artificial intelligence biomarkers for the diagnosis of uveal diseases.
Okay. Good afternoon, everyone. My name is Arshpreet Bassi. I am a second-year medical student, and today I will be presenting my presentation titled The Application of Artificial Intelligence in the Analysis of Biomarkers for Diagnosis and Management of Uveal Diseases, a Systematic Review. I have no conflicts of interest to disclose. The uvea of the eye is a highly vascular structure, making it very susceptible to breakdown of the blood-aqueous barrier and vulnerable to the inflammatory response in case of various diseases. In this review, two major types of uveal diseases were studied, uveitis and uveal melanoma. Uveitis is a common sight-threatening disease that leads to 5 to 10% of vision impairment worldwide, whereas uveal melanoma is the most common primary intraocular malignancy in adults. It has been suggested in many studies that there are several markers that can predict the prognosis, pathogenesis, and treatment outcome of a disease. As artificial intelligence methods are rapidly progressing, breakthrough technologies are changing the landscape of healthcare research with powerful diagnostic and prognostic value. Machine learning methods are employed by AI systems to account for complex interactions, either by collecting input data, including biofluid and tissue samples to predict output values based on new input samples, or by finding underlying patterns in an unlabeled dataset to identify a subcluster or outliers in the data. Although AI methods are well described in other healthcare fields, there is limited information on the value of using AI methods in understanding the complex nature of uveal diseases. Hence, the objectives of this review are to describe the current available literature that describes the application of AI in uveal diseases, identify important biomarkers for treatment, prognosis, and disease profile, and characterize the AI methods used in this field to guide future research. For the methods, we conducted a comprehensive systematic literature search with terms related to the concepts of ophthalmology and AI/bioinformatics, and proteomics, metabolomics, and lipidomics to capture all relevant articles in 5 electronic databases listed on the slide. The search strategy yielded 27,702 articles from all the databases, and after the duplicates were removed, 10,258 studies were screened, and a total of 18 studies met the criteria for inclusion in the systematic review. Data was then extracted to encompass all available information related to study characteristics, including disease of interest, study topic, AI method used, and biomarkers studied. A risk of bias assessment was also conducted. For the results, we found that uveal melanoma and uveitis were the two diseases studied using AI methods in the field of uveal diseases. When the studies were classified by study type, we found that 9 studies were cohort studies, 8 were cross-sectional studies, and 1 was a case report. We found that 10 studies used complex AI methods and 13 studies used regression methods. Additionally, after conducting the risk of bias assessment, we found that most of the studies were of high quality and 1 was of moderate quality. We classified the study based on study topic, and as you can see, most studies focused on disease prognosis, followed by disease treatment, differentiating between diseases, disease profile, and lastly, disease progression. However, in the studies concerning uveitis, most studies focused on disease differentiation, specifically looking at cytokine levels in uveitis presenting diseases such as Beckett's disease, herpes-induced uveitis, and idiopathic uveitis, whereas most studies concerning uveal melanoma studied disease prognosis. Upon characterization of the complex AI methods, we found that principal component analysis was most commonly used, followed by partial least square discriminant analysis. The biomarker sample types most commonly collected was tissue for uveal melanoma in the form of enucleated eyes and aqueous humor for uveitis. Additionally, biomarkers varied across all studies, with the most common being cytokines, metabolites, and proteins. Furthermore, the number of individual biomarkers analyzed varied from 1 to 4,386 per study. Although all except one study found significant biomarkers for their respective study objective highlighting the value of AI in this field, there is little to no overlap in the specific biomarkers found to be significant that allow for definitive conclusions to be made. The only overlap was that of lactate dehydrogenase in 50% of the uveal melanoma studies. Lactate dehydrogenase was found to be an important biomarker for disease prognosis and disease treatment outcome by 4 studies, where one study highlighted that elevated baseline serum LDH was negatively correlated with anti-PD-1 treatment, and the other 3 studies observed high LDH levels with decreased prognosis. Additionally, although there is a large variation in type of complex AI used, many showed strong predictive ability. For instance, although principal component analysis was most commonly used, the value of a random forest analysis was also demonstrated, where with 100% accuracy, elevated cytokines were identified in idiopathic uveitis, highlighting the value of AI methods in analysis. In conclusion, from the current available literature, it is difficult to recognize definitive biomarkers for diagnostic and prognostic application. However, complex AI methods can be used to weigh the merit of significant biomarkers such as LDH. Particularly, complex AI methods can be used in order to create staging tools and predict treatment outcome. Although the information presently available has a large degree of heterogeneity, future studies have the potential of creating impactful AI models that can result in clinical tool development and implementation. I'd like to thank my team and supervisor, Dr. Filfelli, for their support and the audience for attending the presentation. Thank you.
Well, that was a really great talk, Arshpreet. Thank you so much for highlighting these diseases which have a lot of morbidity and mortality in the world population. Just as a reminder to all the audience members, please feel free to type in any questions into the Q&A at the bottom of the screen, and we'll address those in the panel that's upcoming. Our next talk will be from Pete Campbell at OHSU on applications of AI in ROP. Pete.
Thanks so much, Ted. I've really enjoyed this meeting. Thanks for the opportunity to be here. These are my acknowledgements and disclosures. I want to say 2 things. One is that everything I'm going to talk about is really a team effort as part of the IRAP Research Consortium. We've heard from several people today, Jayshree and Mike in particular, but I want to give a shout out to Paul Chan in Chicago and my colleagues in Portland, Aaron Coiner and Susan Osmo. And I do have relevant disclosures as we're hoping to bring this technology to the bedside for care of patients. We've heard a lot of applications of AI that might be interesting and curious, but may not have a clear path in the clinical pathway or a clear solve an existing problem. For example, I'd like to convince you in today's talk that there is at least 2 potential broad motivations for using AI in ROP. One is that the standard clinical diagnosis is challenging, subjective, stressful to neonates, and inefficient. Inefficient because most of the time babies don't actually have disease when you're screening them. And the second is that approximately 50,000 babies a year become blind or severely visually impaired, primarily because they're not screened. So broadly, both as an assistive diagnostic tool to improve clinical diagnosis and potentially as an autonomous tool to screen for a clinically significant ROP, AI may play a role in improving care for ROP. Application number 1 is objective diagnosis. So there are very few vitreoretinal diseases that we diagnose the same way today as we did in 1950. But that's not true for ROP. The ophthalmoscopic exam is the same way ROP was first described by Patz and others in the 50s, and that's the same way we diagnose it today. But all of the components of ROP, that is zone, stage, and plus, are quantifiable. This is an ultra-wide field OCT, which would be one way to provide objective diagnosis. What I'm going to talk about today is using AI to provide objective diagnosis. That is taking a posterior pole fundus photograph, converting that to a vascular severity score, which measures the degree of tortuosity in the back of the eye, or essentially degree of plusness. We've shown that this corresponds to the overall ophthalmoscopic classification of disease, that is no disease all the way through to aggressive ROP. And it turns out this works because the vascular severity score is associated with not only the stage, but also the extent of disease. And it's actually higher in more posterior disease, which tends to be more severe, younger, sicker babies with more aggressive disease. And this has implications for clinical diagnosis as well as clinical trials, which I'll come back to later. We've shown, and others have shown, that the pattern of expert diagnosis, it looks like a spectrum. So these are data on the left from the International Classification Group. 34 experts were asked to classify images to identify standard images of plus disease. And you see a 6-fold difference in the number of images diagnosed as plus disease by world experts. On the right, we show that using AI, we can quantify that spectrum and have it be associated both with the ordinal scores of ordinal classes of no plus, pre plus, and plus, as well as the continuous spectrum. And this concept is now incorporated into the international classification of ROP, which is kind of cool. And images, this figure from the ICROP paper on the bottom actually uses segmentations from our algorithm to sort of demonstrate as qualitatively how this can change. Once you have objective diagnosis, you can also monitor disease. So in the same way that we're now spoiled by using OCT to identify is macular disease getting worse, getting better, how's my treatment interval, all of this other stuff, we can use AI to identify whether a baby with ROP is progressing. Is the stage getting worse? Is the extent of disease getting worse? We showed a few years ago that we can monitor babies and identify up to a month before they were diagnosed with treatment requiring ROP, we could identify disease progression. On the right, we looked in a real world data set of the US telemedicine program and identified over 2 years, 2 babies progressed to require treatment, and both of them were identifiable prior to diagnosis. When to treat. So I've mentioned that inter-observer variability is a problem. We looked a few years ago at could we use this to quantify the degree of severity at which clinical decisions are being made. We found differences both between examiners and within examiners in terms of the level of plusness that people waited for to treat. This has significant implications for consistency of treatment in the real world and real implications for clinical trials, where if these differences between examiners are not controlled for in randomization, which they're often not because these are often site-specific factors, this can lead to unexpected outcomes. Even more importantly, vascular severity and AI-assessed vascular severity may have implications for how to treat. So we know that there's been a change over the past 10 years for more severe disease, more posterior disease to be treated with anti-VEGF as opposed to laser. A few years ago, we showed in retrospective data, so non-randomized, babies in the IROP consortium who were treated with anti-VEGF had higher vascular severity at baseline. They also had more rapid progression of disease before treatment and more rapid regression of disease after treatment. Among patients treated with laser, we found that patients who failed primary treatment, that is, they needed a second treatment, had higher vascular severity at baseline. Either they were treated later with higher stage and extent of disease, or they were treated with more posterior disease. Both of these have significant implications for randomized clinical trials, where treatment failure is one of the primary outcomes. And if you don't control for this, or you have babies not being randomized because they're not, the clinicians don't have equipoise for how to treat, this can lead to, as we're seeing, some clinical trials not meeting their primary endpoints. As I shift towards talking about screening, we've shown in several different populations that AI-based screening could work effectively in practice. So Greenwald and all looked in the US telemedicine data set. In the paper in pediatrics, we looked in India from 2015 to 2017 in 1,254 consecutive exams. Cole et al. Showed it in Nepal and Mongolia, and importantly, this was on a separate camera system in Nepal using the Forest camera, which is relevant because this is a much more available camera in the low and middle income country setting. And then finally, in work presented at APOS this year, in 2 years of consecutive screening in India at the Aravind Eye Hospital, using essentially simulated autonomous ROP screening, we found 99% sensitivity and 62% specificity for detection of treatment requiring ROP, and this could reduce tele readings by 61%. Moving beyond that, could we reduce the number of exams for babies who have low risk disease? I already told you the vast majority of exams reveal no or mild ROP, and I told you that we can identify eye is progressing up to a month before treatment. My colleague Aaron Coiner in work published in Pediatrics said, could we combine these two pretest probability essentially based on gestational age, which is the most important demographic risk factor, and early changes in vascular severity to develop a risk model. And we showed in 2 US populations that this would work. That is, based on a single point in time at 32 to 33 weeks post-menstrual age, we could rule in or rule out babies with severe ROP with 100% negative predictive value. That is, low-risk babies may never need to be screened again. And in work that was published, presented at ARVO and in press soon, we evaluated a similar risk model in India, Nepal, and Mongolia, where obviously the disease is much more prevalent and there are fewer examiners. And we found similarly 100% sensitivity 2 to 4 weeks prior to diagnosis, which could reduce the screening population by 50%. Finally, moving beyond ROP diagnosis, we've heard a little bit about things that we're learning about AI that we weren't necessarily expecting. And Pierce Keen, I think, coined the term oculomics. And so I've shown you already that, for example, if we look at these two babies at 32 weeks, both who are similar pretest probability for developing ROP, risk models can rule in or rule out babies at highest risk of severe ROP based on early changes in the vascular severity. And it turned out the image on the left is a baby that eventually required treatment. This was predicted by the model and turned out to be true. But can we ask different questions? Could we identify other things about the systemic health of the babies? So for example, these are two babies, similar demographics seen at 32 weeks. Can we predict which one of these will have more severe lung disease? And the clinical diagnosis of bronchopulmonary dysplasia is defined by the use of oxygen at 36 weeks post-menstrual age. And so looking at 32 weeks, can we identify which baby is likely to end up requiring oxygen? And it turned out in work by my colleague Pravir Singh, who's a postdoc, was a postdoc in Mass General and now is joining Jay Shri Kalpathy Kramer in Colorado. He was able to train a model using images from 32, 33 weeks to identify which babies would likely develop more severe lung disease. This turned out to be independent of ROP status, which is important because both lung disease and ROP have a lot of similar risk factors. So we're exploring whether this has clinical value, and are there other things like pulmonary hypertension, which may be really relevant for the neonatologist to know that we could identify either using fundus photography or OCT. And so the baby on the left was predicted and eventually diagnosed with bronchopulmonary dysplasia, and the baby on the right was not. In summary, AI can provide automated objective diagnosis of ROP. The ROP vascular severity score may be useful for disease screening, monitoring, objective diagnosis, and treatment. Risk modeling may reduce the burden of exams, especially for low-risk babies. Implementation may lead to autonomous ROP, earlier diagnosis, and reduced risk of advanced ROP. My long-term goal is to put pediatric retinal surgeons out of the business of fixing ROP detachments because they really should be preventable. And finally, fundus photos may contain information relevant to the general health of the neonate. Ted and all the organizers, thanks so much for the opportunity to be here. I look forward to the discussion. Thanks.
Thank you very much for this really important talk, Pete. Our next talk today will be from Minhaj Nur Alam at Stanford University about doing more with less. Minhaj.
Thanks, Ted. Can you hear me properly?
Yes.
Good afternoon, everyone. My name is Minhaj. Today, I'll be presenting our project where we utilize contrastive learning pipeline for robust DR classification. Trying to move the slides. Great. So we all know that DR is a major ocular manifestation of diabetes. Nearly 40 to 45% patients with diabetes are prone to vision impairment due to DR. That's projected to be 188 million in 2019, and by year 2040 is going to be about 224 million. So it's a global pandemic. DR normally has two stages. The early stages, which are characterized by microaneurysms, exudates, etc., are NPDR, and then as it moves to more progressed stages, we can see growth of abnormal blood vessels, and there it goes up to proliferates the retinal tissues, and there can be irreversible vision impairments. So the research challenge is how to improve the treatment management for retinopathies and enable mass screening, early onset detection, and clinical diagnostics. So deep learning models have shown great results for referable versus non-referable DR. We have seen excellent studies where different researchers have used different type of data sets, like open source clinical data sets, and achieved like very high accuracy and AUCs. Traditionally, like the ophthalmic diagnostics workflow has involved imaging biomarkers, integration of computer vision and AI tools, and then clinical validation. Deep learning itself has a lot of different branches, supervised deep learning, and their use of different architectures as well. So in general, when you design a deep learning-based DR diagnostics workflow, we need a good, clean, and diverse data set. We need the associated ground truth with that data set. And then we need a robust deep learning model that can be trained well and then can generalize well, right? So looking at the state of the art, we can make some observations. Is that for widespread deployment, the deep learning models need to be generalized, and more data from different subpopulations normally lead to better model training. However, more data increases the need for more ground truth generation, so which automatically increases the burden to clinicians. So our focus in this project is how to reduce the burden of ground truth generation while developing algorithms that can tap into the large clinical data that are automatically generated within the clinical workflow in healthcare systems or in the hospitals. So that's why we use something called self-supervision. Talk a little bit about motivation, right? So medical image understanding is limited by our annotated data. Like any deep learning model project, we need good data set and then associated ground truths. And our clinicians are already have a massive burden in the clinical side, but in any deep learning based project, they always have to have not only give us feedback, but also they have to sit, and there will be multiple clinicians who have to agree on certain label data or ground, right? And annotations can also be tricky, right? So they have to be expertly labeled by multiple clinicians. Then there would be different strategies in terms of big versus small data sets, and there will be rule-based label extraction for segmentation, etc. They can also be domain specific and style sensitive. However, as I mentioned, there are a lot of unused data that are sitting in our hospital system. So the need to use this unlabeled data is the motivation behind using self-supervision. So what is self-supervision? Basically, in this kind of framework, the supervision is provided by the data, so the need of ground truth automatically reduces. Easy way to give an example is, say I have this data and then I shuffle this and train a model to solve puzzles, right? So in this case, the ground truth itself is the input image. So we don't really need a separate ground truth or label. So by learning to solve this puzzle, the model is learning subtle intricacies and characteristics of this image. And then the weights can be then transferred to a secondary model, and that can do a secondary task like image classification. And since the model already has learned a lot about different imaging characteristics, it picks it up easier, and then we need less amount of data all around. So contrastive learning is one self-supervised model that is based on the contrastive loss. The key idea is same images. For example, like this is from Amani's data set, we have zeros, right? They will have similar embeddings in the embedded space when they're passed through an encoder, and different images will have different embeddings when in the embedded space. We can look at the loss function. So basically what happens is, so this is a loss function. So where we measure for a positive pair I and J, for example, these two, we measure the similarity of them. And then denominator is like average of the similarity function from them, and K is all the other images in a specific batch. So in contrastive learning framework, there should be some mechanism. So contrastive learning is basically focusing on how to distinguish between similar and dissimilar images. And the input of the contrastive learning framework is a batch of images, and the model processes them as pairs, for example, like this, leveraging self-supervised learning. But how do we formulate this? We need some sort of mechanism to get the representation that allow the machine learning machine to understand the image and compute similarity of the two images. So in this contrastive learning framework that was originally proposed by Google 2 years back, so they do transformation and data augmentation. And then after that, it passed through encoder and the projection head, and we get some sort of embedding called ZI and ZJ. For each image, we get one pair. And then based on that, there is the similarity functions are measured. So the hope is that images coming from same image, for example, like these two cats, will have higher similarity, wherever images coming from different images, like for example, cat and elephant, they will have lower similarity. And this similarity is then like combined, and there is a final loss function measured for each batch, right? And then once this framework is optimized, then this representation that has learned a lot about the image is transferred to a secondary task. Now it can be image classification, segmentation, etc. So we adapt this framework for DR classification framework classification task, and we did data augmentation and encoded them and then maximize similarity, and then transferred these weights for downstream tasks. For our case, referable versus non-referable DR. So we learned that normal contrastive learning framework normally uses regular augmentation, like rotating, flipping, etc. But we learned that like for medical images, like retinal images, augmentation and transformation themselves are key to better representation learning. We have to force the CNN to learn more about the shape on top of the texture. So for example, this is a elephant image, elephant skin, and this is a cat. When they're convolved, we see this image, and as a human, we can perceive them as cat very easily. But CNN normally perceive the texture first, and then it predicts them as an elephant. So neural style transfer is an augmentation method that we utilize in our case. So that basically convolves the medical image with artistic style source, and then they generate random environment and random textures. So that really forces the model to learn the shape that are important for classifying different stages. For example, in our case, the retina, we want it to learn about microaneurysm, learn about vasculature, which features will be important towards the classification. Some examples are here, like input image, the style images look like this. This can be totally chosen by you, some empirical methods there. And then the output images are like this. So we incorporated this NST into our framework, and then our results were really, really nice. So we compared fundus net weights, compared it with the ImageNet weights. And to show that it can work with a smaller number of data, we reduced the data set up to 10%, and we validated our data on Kaggle IPAX dataset, and then also validated them on independent, unseen clinical dataset from University of Illinois. So to summarize the results, basically, the fundus net weights perform really better compared to the ImageNet weights, and in both datasets, and even with 10% dataset, it outperforms the ImageNet weights by a greater degree. As the data is reduced, the performance is like much difference between the ImageNet weights and the fundus net weights. So this reduces the annotation effort by almost 90%. Model also generalized really well, validated in the external data set. And so one thing about contrastive learning is that we normally need a larger batch size. So that kind of increases the computation burden a little bit, but that's something like researchers are working on in the future. So thank you for this opportunity, and hopefully we'll talk more in the discussion section.
Well, thank you so much for presenting this work using contrastive learning to significantly reduce the amount of work that needs to go into training these models. We'll hopefully chat more during the Q&A. Next up is Dave Myung from Stanford, who will be speaking about incorporating AI into diabetic retinopathy screening in a primary care network. Dave.
Thanks, Ted, and I want to thank all the organizers for inviting me and all of us here to speak today, this wonderful conference. Trying to get the slide to move. Oh, okay. So yeah, we're talking about, really excited to tell you about the work we're doing, collaborating with primary care and incorporating AI into it, and sort of a real world report on how it works. So somehow it's not advancing. Can you advance the next slide? And no related financial disclosures. Next slide. I want to start by acknowledging the many people in this wonderful interdisciplinary, interdepartmental research collaboration. I want to especially call out a couple of colleagues, Dr. Elliot Dow, who is the Associate Director of this program for the past year, and also our Innovation Fellow, moving on to his Medical Retina Fellowship at Duke. A lot of the work you see here is work that he helped lead, and also Dr. Ted, our esteemed moderator, Dr. Leng, who directs our Stanford Reading Center and helped lead our human interpretation work here. Next slide. So what is diabetic retinopathy? This audience doesn't need to know the details, except to say that here, diabetic retinopathy is the manifestation of diabetes in the microvasculature of our eye. It's staged very specific grades from mild non-proliferative diabetic retinopathy to proliferative and then end-stage TRDs. And our goal as providers between ophthalmologists and primary care physicians is to help prevent the progression of this disease in our patients. We fortunately, in the next slide, have great interventions, lasers, and anti-VEGF therapy, which can help halt or slow down the progression of these diseases. But ideally, we would be able to help our patients avoid progressing further. With diabetes, next slide. These slides just to show that way too many people are going blind from diabetic retinopathy. Way too many people progress from diabetes to diabetic retinopathy in their lifetime. And if you look at the numbers, with all the ophthalmologists we have in the world, the majority of these ophthalmologists would have to spend the majority of their time screening and looking for diabetic retinopathy in the patients. And that's not to say the other diseases that we are looking for and try to treat. So there's clearly a load issue. The population is growing of people and diabetics, but the population of our physicians to treat them are not. Next slide. Okay. All right. So what we're doing, we start at Stanford. We started with many other places have done is a telemedicine-based way of screening for diabetic retinopathy. In primary care clinics, we put a non-mydriatic fundus camera. And then we have remote readings, telereadings by our retina specialists to look for the disease. We set up actually initially five cameras around the Bay Area. Those images were taken in primary care. Dr. Lang and his colleagues and in our retina division would read the images, and then we'd send a report back to the primary care physician what to do next. What helped drive the success of the initial program and moving forward was that our primary care doctors are actually beholden to this key measure, the HEDIS measure, health effectiveness data and information set, a series of care measures that they have to provide for their patients, provide optimal care. And one of those, which is out of their control, is actually the eye exam. So we can't necessarily force patients to see their retina doctor or an ophthalmologist. So we thought, well, if we provide telecare, can we help them do that? And we found we were able to screen almost 1,000 patients. There is obviously a telemedicine workflow, CPT code, and so forth for that. It was very successful, though we found that there are ways that we can improve the success of this workflow. And we thought that at the time in mid 2020 that our AI could do this. And what allowed us to do that was the fact that the HEDIS measures at that point were then declared that they were going to allow AI exam to satisfy those measures for primary care doctors. And then the CPT code 92229 was then put into effect. So that sort of opened the door for us to then incorporate AI, and this in our case, the IDXDR system. And how does AI work? I mean, we have a lot of presentations today on how it generally works to detect DR. It's a biomarker detection process where it detects the stigmata such as hemorrhages, microaneurysms, exudates, and so forth, and then comes up with an assessment and decision. The IDXDR system, which was the first cleared by the FDA in 2018 in all of medicine, essentially creates a binary result, whether you're negative for more than mild DR or positive for more than mild DR. And in our framework, we put it, we actually layered on top of our telemedicine framework. So we had the system take the photos and go through a quality module, determine whether the quality was sufficient, and then come up with the diagnosis and the referral decision. We layer on back into that an overread process where more difficult to read images were then forwarded to Dr. Lang at the Stanford Reading Center, and then the diagnosis and recommendation made from there. And so we have an amazing information technology group here at Stanford. And so together we've put together this program we call the STATUS program, the Stanford Teleophthalmology Autonomous Testing and Universal Screening Program, STATUS. So patients know they can get the status of their eye checked at their primary care physician. And here is actually all 1,200 patients that we screened and where they live in the Bay Area relative to their primary care doctor's office, and also relative to ophthalmologist office, including the Byers Eye Institute. So we can look at usage patterns, referral patterns from there. We're still digging into this data, and it's very exciting to be able to do this. Here's some screenshots of the report that comes out of the IDX system and how it integrates into Epic, which is done very smoothly. And actually, the AI result comes out much like a lab result, like you're getting an A1C done or a syphilis titer done. It's very easy for the primary care physician and the ophthalmologist to follow. Here's some images of our the launch of our first camera when we started a telemedicine process. In 2020 was a busy year. We launched right around the time COVID started. It was four of the cameras were launched in the UHA, University Healthcare Alliance system. And then end of 2020, we launched the first IDX camera. And then in early 2021, last year, we then equipped all 7 sites with the IDX system. And here's just some of the data comes out of it. We can track monthly, actually on a daily basis, how the process is going, how many exams are being done at each site, how they compare to each other. Here's another representation of that. And I just want to show this next slide, these next couple slides, just how how the demographics of our patient population look. So, our mean age is around 58, 59 years old, and about 11.9% of all encounters were positive for more than mild DR. Demographically, our population is roughly a third Asian, roughly a third white non-Hispanic. And you can see here, there really is no, everyone essentially is a minority in the Bay Area, which is very different, I think, than other parts of the country, and that has implications on how the system may play out. And this is probably the most important slide, showing this HEDIS measure I mentioned, the percentage of patients who get their recommended annual eye exam. We chose clinics that, on the blue line, are the clinics that we pre-chose that were struggling with that in that regard. The yellow line is the 90th percentile target for these primary care clinics. And as you can see, it was below that line. Whereas we compared to those who we did not layer on top telemedicine or AI, as you can see, over the course of the last couple of years, you see the ones that incorporated telemedicine and the AI system gradually increase and now are well over the 90th percentile mark, whereas those that did not, interestingly, have struggled. And so this is a great evidence to us that the great improvement in quality of care we can provide through integration of AI and telecare into the system. So we are now actually planning to expand from 7 to 10 total sites in the Bay Area, including the main hospital and a few other sites along the peninsula in the South Bay. So in conclusion, I could say that feel that AI helps to greatly expand access to necessary eye care for diabetic patients. We think it's kind of like a load sharing concept. Dr. Campbell mentioned reducing the burden of telereadings. So basically, it's a load share. AI and human intelligence work together to screen patients for this disease, and with an overall gradability of over 96%. We do believe there's still ways to improve the process. Workflow enhancements can improve screening efficiency and volume, getting the word out. There's a real collaborative effort to outreach to patients, showing them that this is available, allowing patients to actually even schedule their own appointments on their own into this program. And in close collaboration with your institution's IT, can help track program metrics real time and look at referral patterns and so forth. So I want to thank everyone for their time, and I also especially want to acknowledge the team that we work with, and as well as our wonderful retina colleagues at the Byers Eye Institute, without whom none of this is possible. Thank you.
Thanks so much, Dave. This has been a really wonderful presentation of a real-world implementation of an AI screening program in a probably a very logistically complicated academic setting and network. Next up, we will be continuing the retinopathy series here, hearing from Amani Fawzi about the application of OCTA. Amani.
Thank you so much, Ted, and the organizers for including me in this exciting session. I learned a lot from the previous speakers and previous sessions, and I look forward to sharing with you my results. So we wanted to look at OCTA's ability to predict progression in diabetic retinopathy, and we were most interested in augmenting our work with some AI algorithms. So to frame the problem, really, if you think about moderate and severe diabetic retinopathy, that highly enriched, high-risk population that we're all talking about today, the risk of progression to PDR is anywhere from 12 to 56%. So when a patient's in our chair, it's really hard to know which one of these two patients is going to progress in 1 year. And wouldn't it be nice to have better predictors for those who will progress? So from our classic progression sort of studies, from population-based studies, we have the risk of the glycemic load is this highly enriched predictor, but it only explains about 11% of the risk progression. Other population-based studies provided some metrics, but none of them are applicable on a patient basis. So there we thought that perhaps OCTA can give us another metric to identify these highly enriched high-risk population. So we focused on treatment-naive eyes with moderate to severe NPDR, who in our practice had baseline OCTA. They had to be treatment-naive, no previous treatments. And then we looked at those that followed up in 1 year and had either progression to diabetic macular edema or proliferative diabetic retinopathy or not. So we identified a population of 45 eyes, of whom 15 progressed to complications. And we wanted to look at this population of progressors and non-progressors to see if OCTA provided a clue to who's going to progress. So in terms of OCTA metrics, we really got excited about this new metric developed by Fujimoto's group and Siu, who used to be a PhD student at Northwestern. And here they really incorporated this physiologic metric of oxygen diffusion distance. So any part of the tissue that's 30 microns away from a blood vessel is thought to be ischemic. So if you incorporate that into OCTA, you'll see here on the top, all of these red and green areas are various distances away. The redder, the worse or more ischemic in the retina. So we thought this would be a very interesting metric to apply. So before we could include it in our data set, we had to develop our own algorithm for automating this rather than having to do it manually. And Janice Ong, one of our brilliant medical students, developed an automated algorithm to move the speckle and skeletonize the vessels and sort of highlight this this areas of perfusion deficits in our OCTAs. So we wanted to look at the demographics of our populations and make sure that aren't any inherent differences between the population that develop complications. And interestingly, the only significant difference was male gender. So males were more likely to progress to complications. And even more interestingly is a severity of baseline retinopathy wasn't really different. So whether you had moderate or severe wouldn't totally predict progression, which is the reason why we wanted to develop this algorithm. So when we looked at our classic vessel density metrics, it turns out that the deep and the middle capillaries were very significant. So the more ischemic they are, the more likely people would progress. And then when we compare that to our GPD or the novel metric, we see similar things. The middle and the deep capillaries, when they're more ischemic, these were the patients that were more likely to progress. So to look at an example, here's an eye that did not progress. And as you can see, there's highlighted in red the areas of GPD deficits. And you can see that there's a moderate number of these deficits. But when you compare that to an eye that progressed, there was really a larger amount of red areas in the deep capillaries, consistent with more ischemia at the deep capillaries. Next, we wanted to look at the accuracy of these algorithms. So we looked at the ROC curves, and what you see here is for the classic vessel density metrics, the deep capillaries had the highest AOC. And when we look at the GPD metrics, and the next higher was the MCP. So again, in the deep complex, that was where the money was. And when we looked at the GPD metric, it was similar. The DCP had the highest metric, and here it was slightly higher than when we looked at vessel density alone. It was 94. The AUC was 0.94. And the second best were again the MCP and the whole retina GPD. So with that, we thought to try to think about a metric and how to implement it in clinical practice. So could there be a number that we could give clinicians to look for to identify these high-risk patients? And it looked like 12% or 13% of the DCP GPD would be a good number to hang your head on, or 28% or so of the DCP, and that these would be highly predictive. And so what is it about the deep capillary plexus that makes it so highly predictive? And if we look at the work by Tim Kern, he showed that the photoreceptors are really the highest producers of oxidative stress in the retina in a diabetic eye. So perhaps the presence of oxidative stress in the deep retina close to the deep capillary plexus could be contributing to this. And if we think of the location, so these oxidative stress markers would first affect the deep capillary plexus, and they could be toxic to these endothelial cells. Other parameters, if you think that the photoreceptors will affect the deep capillaries, we know that the deep capillaries also supply oxygen to the photoreceptors, especially in dark. And that was sort of the impetus for wearing goggles at night for ROP or for diabetic retinopathy. And if we think ischemia at the deep vessels is leading to VEGF, and VEGF then dilating the superficial, and then the superficial vessels could then further exacerbate ischemia by stealing oxygen and blood flow from the deep. So there's many, many levels where this ischemia at the deep could be toxic or may predict progression. And so it didn't matter if you were looking at GPD or vessel density, the deep capillaries seem to be a very high predictor for these eyes that are higher risk. And ischemia at the deep plexus may be telling us a lot more about the eye than other parameters, perhaps. And so next we wanted to see if we can enhance our population by involving more patients and tweaking our algorithm. And as Dr. Chang and Dr. Kalpathy Kramer talked about, this patient access to their data safety, data privacy is really a key factor in the ethics of AI. So would there be a way to collaborate with other institutions without actually sharing any patient data? And here, Dr. Kalpathy highlighted this as Federated Learning brings that solution, perhaps. And so if you think of classic collaboration where two institutions would basically share their data, and maybe there's a third institution that analyzes the data and applies the AI algorithm, contrast that with federated learning, where no patient data leaves any of the institutions. Instead, they're only sharing the model with perhaps a central center that optimizes the model, collates it and sends back a new model that's better, or a sequential system where each institution serves the model sequentially with the other until they collaboratively reach the final model. So that seemed like a very exciting application, as Dr. Kalpathy told us that this COVID was a very, very fertile ground for applying this. And as she also told us, a lot of these algorithms looked great on paper, but then for various reasons, they did not reach their full potential. So this is our project. We started this because of Marinko, who at the time was still with Simon Fraser and his postdoc student. They shared with us an algorithm that two of my medical students worked on. I could tell you that the majority of the time were spent on harmonizing the data, curating the data, labeling the data, which speaks to all the problems discussed in the previous sessions. And so the model was shared with us and another institution, and each of our institutions then generated the updated model. And because we took so much time to curate the data, we haven't gotten further. And I look forward to sharing with you the results later. next year perhaps. And where does federated learning come from? That I learned while researching this talk. Apparently Google developed it, and the first description was in one of their blogs. And here they wanted to solve this problem of having iPhone or smartphone users develop algorithms without ever sharing their user data. And it's applied in a Google algorithm where it auto-completes your searches. And the first application was a year later in the medical field in 2018. And so in summary, I believe that federated learning has a lot to offer us for facilitating collaborations between institutions, solving the problem of generalizability and bias by allowing multinational institutions with a diverse population to collaborate. The teams have to be very well versed, work well together, and taking time to do a good data curation and harmonization is very, very important. And finally, I thank you for your attention and thank my collaborators and my students who worked hard on this project.
Thank you so much for that talk, Amani. Very important topics to revisit later, both the OCTA as well as the federated learning. As a reminder, please feel free to enter questions in the screen below your video there. And up next will be Justin Liu, who's a high school student from Southern California, and we'll be talking about ensemble methods for machine learning. Justin.
Thank you very much, Dr. Long, for the kind introduction. I'd like to begin by expressing my gratitude to everyone and the meeting organizers for giving me the opportunity to be here today as a high school student. I'm truly honored to be part of the summit. So I have no financial disclosures, and my research was on developing INET, a machine learning ensemble for the efficient and interpretable diagnosis and lesion localization in diabetic retinopathy. So DR is a devastating eye disease that is a leading cause of blindness. Blindness from DR can be avoided, however, via early detection, and so regular screening is truly vital. But currently, a large portion of the diabetic population doesn't have the resources to get their eyes examined on a regular enough basis, which is in part due to the deficiency of ophthalmologists. And as was demonstrated by this study, there is less than one ophthalmologist per million population in 23 countries across the globe. And even when ophthalmologists were available, a team at Google found that they were sometimes inconsistent with their gradings of patients' images. So as you can see, the black rows here show how one patient's image was given a red grading of proliferative DR by one doctor, and then it was given a blue grading of healthy eyes by another doctor. But meanwhile, AI can be an instrumental tool for offering an alternative form of DR screening that can complement existing methods and ophthalmologists. So shown here is my overall pipeline for the first phase of the study. Data was first obtained, then pre-processed and used to train 24 image classification networks. And finally, an ensemble learning model was created to output a binary diagnosis, as well as 4 explainability visualizations. I began developing the diagnosis engine by leveraging the Asia-Pacific Tele-Ophthalmology Society dataset, or APTOS, which contains a total of 3,662 fundus scans graded across 5 levels of severity, ranging from 0 all the way to 4. And then to correct for the uneven number of images per each class of severity, I converted this into a binary classification task, with one class being the images graded as 0 or healthy, and the other classes being the images graded as any value from 1 through 4, indicating some level of DR being present. I also used a class-sensitive focal loss function to further address any class imbalances, and then subsequently trained 24 state-of-the-art image classification frameworks, including the previously unconsidered EfficientNet and MobileNet families. And then, as mentioned before, leveraging an ensemble stacking technique, I fused the top 4 individual models into a higher performing classifier. And the generation of the ensemble model's explainability visualizations is mostly governed by these 2 equations seen here. These visualizations localized regions of affection and helped eliminate the black box of machine learning, since we often only see the input and the output of an AI model and not the hidden processes that occur with it. And for feature engineering, I derived 16 different image processing filters to enhance important image features within a patient's fundus scan, such that they were easier to detect by my computer models. 9 of these image processing filters were the first to be used in DR. And the filters are seen on the right, with the saliency procedure used to calculate the last map right there. And then moving on to the next phase of this project, which was lesion localization. This study from Saudi Arabia is currently the only lesion localization study that has adopted the YOLO computer vision algorithm. More specifically, they used YOLO v3, and they trained a couple of variations and achieved a final mean average precision, or MAP, of 0.216. So in my study, I designed 3 custom YOLO algorithms that could detect lesions faster than traditional object detection methods that didn't use YOLO, concurrently tackling the small object problem and optimizing ink boxes to detect differently shaped lesions. So the algorithm uses a series of convolutional blocks to mathematically encode an input image into a 3D volume, which is seen in yellow there. And as the diagram suggests, each grid cell in the original image is transduced and represented in the final sub-volume output, which is in turn composed of 9 concise features that encode P sub C, the probability of whether the algorithm thinks it detects an object in the box, B, the coordinates of the box, and C, the class confidence scores pertaining to 3 classes that the algorithm is trying to classify in between. And then finally, to simplify the outputs from my model to enable a more accurate interpretation, I fused overlapping boxes by removing those with a low confidence score through non-max suppression, or NMS. But because NMS experiences a major flaw in that it sometimes deletes an object in close proximity to other objects, even if it is a correct prediction, I made use of soft NMS to preserve an overlapping box as long as its initial confidence score was higher. So now moving on to the results from the study, the table contains the performance metrics of the 25 classification models trained, with the models achieving the highest metrics highlighted in yellow. ResNet50 v2 achieved the highest accuracy, F1 score, and Cohen's kappa. Diffusion at B7 achieved the highest precision. DenseNet 169 achieved the highest sensitivity. And comparatively speaking, MobileNet v2 actually had surprisingly impressive results considering its small network size and low number of parameters. And then the Ensemble model seen on the bottom, consisting of the top 4 models, yielded the best results compared to any of the individual models, which reinforced the idea that Ensemble learning was to avail. Next, it was found that applied in conjunction with contrast-limited adaptive histogram equalization, or CLHE, the YCBCR color space augmentation was the optimal feature engineering filter of the 16 I performed experimentations with. And I theorized that this filter's high performance was due to its slightly more innovative inversion of colors that no other filter really offered. And then canny edge detection suboptimal performance seen on the bottom in red, maybe attributed to the fact that it oversimplified an image down to only the blood vessels, which isn't useful for detecting all levels of DR. And transitioning to INET's explainability visualizations. So the first row here is the patient's original fundus scan. And then after passing it through my computational pipeline, which runs from the top row down to the bottom, the diagnosis engine was able to stage by stage locate retinal abnormalities. And as you can see, 2 very distinct lesions in the top left. They're a little hard to see on the slide, but the 2 lesions on the top left, were successfully filtered out and enhanced after this process, seen in the bottom row there. And these right 2 columns depict healthy eyes, so that my model did not detect any abnormalities in the final output seen in the bottom 2 black squares. And likewise, Shapley value analysis was able to draw red dots in the precise locations of some retinal lesions for the DR cases seen in the left 2 images, while no lesions were detected in the healthy scans portrayed in the right 2 images. And lastly, for further qualitative assessment, INET's intermediate activation maps showed that each convolutional filter picked up on unique pixel patterns and became increasingly abstract or convoluted as they progressed deeper into the network. So in this case, from layer 22 to layer 80. And this really reaffirmed trust for the computer models because it kind of emphasized how they learned over time. So the ULO V5X lesion localization framework was found to be the highest performing model out of the 3 I trained, reaching a final mean average precision, or MAP, of 0.265. And this was actually a 23% increase in accuracy over the prior YOLO lesion localization study shown. The algorithm was able to draw bounding boxes around microaneurysms, hemorrhages, cotton wool spots, and hard exudates. A prominent example is seen in the middle, where a hemorrhage was precisely localized and labeled by my algorithm with a confidence score of 89%. And then observed in this before and after illustration, the soft NMS technique successfully coalesced extraneous bounding boxes, which enabled for a more accurate interpretation by either eye doctors or patients alike. So in summary, this project consisted of two primary phases. First, the diagnosis engine involved training 24 models, of which the top 4 were used to form an ensemble model that attained an F1 score of 97.8%, and that could also generate explainability mappings. And MobileNet framework, the MobileNet framework postulates deployment onto embedded devices as a promising avenue. Second, the lesion localization framework trained 3 custom YOLO algorithms that localized 4 different types of lesions, achieving a final MAP of 0.2653, which was a significant improvement over prior works. Finally, this work wouldn't have been possible without the continued mentorship of Professor Jorge Quadros, as well as the expert ophthalmic interpretations from our very own moderator, Professor Lung, as well as the support from my high school science research teacher, Miss Melissa Grace Close. This research was also presented at ARVO 2022, and I hope to continue the project over the summer, hopefully with academic and industry collaborators for AI-related research and beyond. I was honored to have presented today, and thank you so much for letting me be a part of this amazing event.
Great talk, Justin. Thank you so much for sharing the work you're doing there. Our last speaker of this session will be Amita Domapalli, who will be talking about automated classification of DR severity score for clinical trials.
Thank you for the opportunity to present today. I'll be talking to you about automated classification of diabetic retinopathy severity score for clinical trial eligibility. My name is Amita Domalpalli. I'm the director of the Artificial Intelligence Research Unit and the research director of the Wisconsin Reading Center. I have no financial conflicts of interest, and here are my co-authors. We're all very well aware that AI for screening diabetic retinopathy uses single field images. So these are images that are centered on the macula. It's just a single image, could be a wider field, 40, 55 degrees, but they're all just single images. And they're mostly used to determine referable versus non-referable diabetic retinopathy. Clinical trials, on the other hand, use different imaging protocols, and they use what are called the 7-field stereoscopic imaging protocol, which require multiple images, essentially 7 areas of the retina that are imaged using stereoscopic imaging. So there's pairs, so there's 14 images. And graders review these 14 images using stereo viewers to arrive at a scale called the Early Treatment Diabetic Retinopathy Severity Scale. Now, the ETDRS scale is also used for inclusion-exclusion criteria for clinical trials. In diabetic retinopathy prevention trials, the moderately severe to severe NPDR eyes are what are commonly included, and reading centers receive these images from clinical sites, confirm that the eye has the sufficient level of retinopathy, and then confirm inclusion in the trial. The estimated screen failure rate for images submitted to the Wisconsin Reading Center is about 50%. So 50% of the time, the graders look at the images and say do not meet the criteria of the study. And the most common reason for failure is the eye not having sufficient NPDR levels. So it's less than level 47. So this is an ordinal scale, although the numbers are not continuous, and it goes from DR absent to advanced PDR, proliferative diabetic retinopathy. So the retina specialists are really good at ruling out proliferative diabetic retinopathy, but distinguishing various severity levels of non-proliferative diabetic retinopathy doesn't go so well in the clinic. There isn't time to go through these images in detail and arrive at a ETDRS level. So our goal was to see if can AI assist retina specialists in screening for clinical trial inclusion-exclusion criteria. So this is an example of images that are montaged. So these are 7-field images that are montaged. On the left panel shows images that are less than 47, less than moderately severe to severe NPDR. So those would be considered not eligible. The center panel shows an example of a montage of 7 fields showing an eligible eye, and the right panel shows eye with PDR, so proliferative diabetic retinopathy. And in general, the clinics are very good at ruling out those. So we sought to just distinguish on a binary scale, not eligible or eligible in a set of eyes. So our thought was that we need to establish AI-assisted pre-screening, and to reduce the burden on both the patient, photographer, site coordinators, and the PI, we said, how can we make this simpler? So we know that we need these 7 field images to arrive at this elaborate ETDRS scale. And so to simplify this, we said, okay, can we come to this levels of 47, 53 together as the binary scale? Does the eye meet these criteria or not? And can we use just field 2 so that patients don't have to go through this extensive imaging protocol only to be screened out? To take this further into a workflow, if this field 2 is submitted to this algorithm and the AI model says, yes, patient is eligible within the range, then the photographer can proceed with 7 field imaging, give it to the reading center graders to further confirm eligible or not. However, if the AI model determines that the patient is not eligible and screens out, then the patient remains ineligible. So we used training images within the reading center for training an efficient NetB4 model. It was an 80-20 split. Our outcomes were, is a patient ineligible or eligible based on the ETDRS level. And we used 440 field 2 images for training and 132 for internal validation. The ground truth was reading center grading using all 7 field images for ETDRS level. Here are our results. Again, it's based on AI assessment based on a single field and a grader assessment based on multiple images. The accuracy of the model was 86.4% with a sensitivity of 0.77 and specificity of 0.89. I'd like to draw focus to the false negative rate of 22.6%. So 6 eyes in this data set were predicted negative by the AI, even though they were considered to be eligible by the graders. And we were kind of concerned about this number because these are the patients who will never be reviewed by a reading center grader. So if the AI predicts as eligible, so predicts as positive, they go through the reading center workflow for further confirmation, but the predicted negatives don't get a second look. And so these are lost patients for clinical trial, and we know how precious patient recruitment is for clinical trials. So we don't want to be losing 20% of the patients on a false manner. So we looked at reasons for false positive and false negative predictions. For the false positive predictions, which again go through a second look at the reading center, the problem was that the pathology was predominantly within field 2 in about 60% of the eyes, and image quality was a reason in 40%. For false negative predictions, the pathology was predominantly outside field 2 in a couple of eyes in 30%, and image quality was a majority of eyes. And I'll go through what these pathology outside, inside means. So here's an example. The white circle again denotes what field 2 is. And you can see in this montage that most of the disease is happening outside that field 2. And so when the AI sees only that field 2, it thinks there is really nothing much happening in the eye, whereas the grader gets to look at all those outside areas and determine a higher level of retinopathy. So the AI sees nothing and says the patient is not eligible, no retinopathy or very mild retinopathy, when in fact the patient may have qualified because of pathology outside. So in this case, the AI is undercalling diabetic retinopathy. Here's an example of false positive. Within that circle, you can see there's hemorrhage, and so the AI expects, I guess, more pathology outside, but in this patient, there is nothing much happening. Apart from that hemorrhage there is no other activity outside. So there's this imbalance between central and peripheral fields with more pathology in the central field, and the AI overcalls retinopathy. Poor image quality. Here are some examples of poor focus and poor illumination. With image quality, it's a little more tricky because we know how image quality affects human analysis or evaluation of retinopathy, but I'm not sure how this affects an AI assessment. So to conclude, the AI algorithm can identify eyes with DR levels less than 47 with good accuracy. AI pre-screening for eligible participants before grader confirmation can reduce screen failure rates. So this pre-screening model, and it can create cost efficiency, reduce burden for participants and clinical site staff. So real-time automated assessment for potential eligible participants could improve enrollment in DR clinical trials. So false negative rates need to be kept at a minimum in these pre-screening models because they do not get further assessment by human graders and are excluded from trials. And we also have to do external validation on this model. Our goal would be to do this in a prospective trial, comparing the traditional grader-only approach versus having this tiered approach of AI and grader combined. Thank you, and I'm happy to take any questions.
Thank you so much for this wonderful talk. And we're going to be moving on to the panel portion of session 5 here. If all the presenters will just unmute themselves. My first question actually is for you, Amita. We saw earlier today the presentation from 2 corporations that have FDA cleared algorithms for detection of diabetic retinopathy. And I do believe that in their clinical trials, they did use a 7-field gold standard to test their algorithms. But their algorithms, from what I understand, just uses a foveal-centered image and a nerve-centered image. And so do you believe that they are missing some cases of more severe DR? And how is that compensated for, I guess, in their clinical trial design?
I totally agree with that, Ted. This is something that we probably did not think of when comparing single field to 7-field, but whatever problem we encountered in our project is the same thing, same problem that all the FDA validation trials would have been going through. What we have not done is kind of annotating lesions or having the grader give an estimate of, I feel, just like how in ultrawide fields we use the predominantly peripheral lesions kind of thing. In a 7-field or a 4-wide imaging, are the lesions predominantly outside the center? That would be something to look at, and that could be a reason. I'm sure, both Abramoff and Solanki and everybody, they've thought of these as a potential issue for overcalls and undercalls.
Yeah, I think it's potentially an issue with these automated systems for doing these mass screenings worldwide. Pete, I had a question for you. I was really interested when you mentioned that there were some eyes that were treated with anti-VEGF having more posterior disease. Have you guys started looking at modeling eyes who have previously been treated with anti-VEGF and how that would play into the prediction for recurrence of, we know that a few weeks after you treat with anti-VEGF, there's the potential for the RP to come back. Have you guys looked at that?
Yeah, thanks, Ted. That's a great question. The short answer is yes. We looked in our data set, although in the IRAP data set, we didn't have a ton of reactivations that were captured by images, but I'm working with some colleagues, Andreas Stahl in Germany on the CARE-ROP data, and we have analysis of that, which is a randomized controlled trial of ranibizumab that actually shows higher vascular severity score at baseline is associated with increased risk of needing retreatment in the future. Which makes sense intuitively with what we know about ROP, with clinical practice patterns. Those data are not yet in press yet, but they will be hopefully available soon. So I think the answer is yes, and I think that it has implications for clinical trial design because a lot of people are moving away from treating the most posterior disease with laser, which means that your failure rate for laser may be lower in the average patient randomized in some of these trials we're seeing. So I think there's a lot of room for improvement as you move from sort of qualitative to quantitative and sort of subjective to objective diagnosis.
Thanks. Thanks for that, Pete. Amani, I think you touched on two topics which I'm really interested in, which is OCTA as well as federated Learning. I have some questions about both of those, but first, with regard to the OCTA, those of us who work with that data know that those images are quite large and a little bit unwieldy for machine learning ingestion, I guess you can say. Did you circumvent that by just outputting the capillary plexus as like a two-dimensional image and then putting it into your model? And if so, do you feel that there might be a future where there can be more automation? I think going from the direct raw data directly into the models.
Yeah, that's a great question, Ted. And in fact, we did do that. We did basically simplify the process by taking just slabs of the deep and the superficial to implement into the model. And I think there's definitely room, because in 3D, you'll see a lot more going on than there's superficial and deep. And hopefully we'll have more powerful algorithms that can deal with this complex 3D data in the future.
Thanks. And on the federated learning part, congratulations on successfully executing a federated project. Those of us who have attempted them or dreamed of attempting them have run up against a few barriers, most likely contractual and logistical in nature. Can you just walk through some of the challenges that you had in your institution and how you overcame some of those barriers?
It was actually much easier than I expected. Once we explained to our IRB what's really going to happen, that our data is never going to leave our institution, and that the only thing coming and going is the AI algorithm, basically, we got an expedited approval. That was not our hardest problem. In fact, I've had a lot harder problems sharing data with international sites. Because little did I know that in Europe, they really have very strong feelings about sharing data with US-based researchers. So it's really a cool and very efficient problem, a solution for that problem. So I'm sorry you're having these issues with your institution.
Thanks for that. I'm not the only one, I think, that's having issues. I think if you ever try to work with a non-academic institution, then and you're trying to collaborate between corporations and nonprofits, there then become intellectual property concerns, I think, even if no data actually leaves each person's bucket.
It's true. True. Yeah, we haven't gotten that far. We're still sort of in the initial phases. We haven't gotten the modified algorithm back, so it's still a work in progress. And then I think the IP issues is something I hadn't thought about. So thank you for bringing that.
Hopefully you won't have a hard lesson on that in the future as you start to negotiate new contracts. Minhaj, I really enjoyed your talk, applying this contrastive learning approach to ophthalmic images, and obviously it comes from a non-medical background. Do you see any challenges for the medical community or the FDA or general public actually in accepting algorithms trained, using, not essentially data that's not of the subject itself in making medical interpretations?
Thanks, Ted. Yeah, I think the way we need to look at it is not really the focus should not be on non-medical data. The focus should be how we're using the non-medical data to kind of transform or augment the images. Actually, there have been some cases have actually used, say, medical imaging images and non-medical images for this augmentation task specifically, like for object detection. And since these non-medical images offer more diverse spectrum of textures, so that really helps in our task. So I think it's like how we present this is not, the focus should be like why we're doing this and like why this helps the overall like machine learning framework. So yeah, I see like there have been some papers already, like they're looking at medical images and like using this kind of like contrastive learning framework or augmentation technique. So I think it's a growing piece of like research field. So I'm really excited about it. Like any unsupervised methodologies. Actually.
Yeah, I think certainly reducing the burden of finding labeled data, it would be a benefit to the entire field of training, especially in ophthalmology. I had a question for Arshpreet about your topic of ocular melanoma. As we know, it's a potentially very devastating and lethal condition. However, the prevalence of that disease is much, much lower than the other things we were talking about in the session, being diabetic retinopathy, which is a huge, huge burden in the world. But because melanoma is less prevalent, there's less training data out there. Now that you reviewed all these models and other papers, how do you think those model developers will approach this issue of not having much training data?
Yeah, I think that was an issue that we came across. We did do a bigger systematic review, and we found a lot of data on like diabetic retinopathy or like glaucoma, for instance, and there was this issue. So I think just having research like this to identify the gaps will allow researchers to like further conduct more research in this area.
And also, how did you distinguish what a complex model was from ones that weren't complex?
So we actually distinguish between machine learning and statistical methods. And so machine learning methods, as we know, is used to predict future relationships, versus statistical methods are used to make inferences about relationships present within the data itself.
Thank you so much. Justin, I really applaud your use of explainable features to describe what the machines are doing. I think these types of approaches are really necessary to gain, again, a medical community trust as well as public trust in the ability of these algorithms and machines to actually identify what's happening in our bodies. Why did you think that the YOLO algorithm in your study actually outperformed the other ones as far as localizing these lesions themselves?
Yeah, so for YOLO, when I trained the model, I really made sure to use a diverse array of data augmentation strategies so that we could create more instances of data, because the DDR dataset that I used only had like around 700 images, which isn't optimal for training any machine learning model. So on top of data augmentation, I also used learning rate decay so as to prevent exploding gradients, which would inhibit further learning in the machine learning process. And then probably the most important thing was anchor box optimization. So instead of sliding a conventional square block across an image in hopes of detecting an object within that image, I optimized the shape of the sliding window through anchor box optimization, which I think probably allowed the algorithm to detect differently shaped lesions. For example, like horizontal versus the vertical lesions could have differently sized boxes and sliding windows.
Wonderful. Pete, another question for you. Getting images from these babies is technically challenging at times. Are you using different camera types and platforms, and are you seeing any differences? And do you think validations need to happen between those different camera platforms on algorithms trained on other platforms?
The answer to the last question is absolutely. I mean, we've heard throughout this morning that that the external generalizability is not always high when models move from one population to another for a variety of reasons. We've seen the algorithm work fairly well across demographic populations, but most of the data has been on the RetCam, with the exception of the one paper we published on the forest camera. This is the elephant in the room in terms of secondary prevention of ROP and diabetic retinopathy, to be honest, because as you and others have shown, telemedicine is effective. You don't need artificial intelligence. And so that's why I think we all need to be a little bit humble in terms of saying this is going to change anything, because it's all dependent on the infrastructure for telemedicine being in place. And so I think for these technologies for diabetes to work, for these technologies for ROP to work, we need to develop systems of care that aren't dependent on really high cost cameras to really scale and be sustainable. And so, yeah, I think there's a lot of potential for lower cost ROP cameras, whether those be smartphone based, as work done by Stanford and others, or lower cost contact based cameras. I think that we're going to be seeing some progress in that area and really hopefully improve care delivery in that way. But yes, all of the AI needs to be validated on the actual equipment and populations being studied and used on.
Thanks, Pete. Amita, we'll close with you with one final question about image quality, I guess. Were patients all dilated or undilated in the work that you were doing with your 7 fields and comparing them to the 2 fields? And do you think that's an issue as far as what type of image we're using for training, whether it's coming from an undilated or dilated pupil?
Yeah, so the images we used were, so from the 7 field images, we pulled out the single field and used it for the AI training. So they were all obtained from dilated protocols. So, clinical trial, fully dilated protocols. But I do think, research has shown that models trained on dilated images don't work as well on undilated. And if in this pre-screening model, we're hoping to get a quick look-see, take an undilated single field, submit it, pre-screen, and then go ahead with the fully dilated imaging protocol, we don't know if this will work. So definitely not just cameras, but dilation is also important. There's just so many factors we have to take into account to fully validate a model.
Thank you so much. I'd like to thank all our panelists and speakers today for their contributions to this meeting. It would not be a success without you. So have a great rest of your weekend, and we're going to move on to our final session, session 6. Our first speaker will be David Lee, who will be speaking about machine learning for differential artery and vein analysis in OCT and OCTA. David.
Thank you very much. Hello, everyone. I am a student of Dr. Shin Shanyao's lab, and I will be taking his place. We are from the Department of Biomedical Engineering at the University of Illinois at Chicago. Today, I will talk about our lab's research in machine learning for differential artery vein analysis in OCT and OCTA. There are many imaging modalities that can be used to visualize the retinal vascular changes from different eye diseases, such as fundus photography, optical coherence tomography, OCT, and recently, OCT angiography, OCTA. OCTA is an imaging modality that can enable 3D visualization of individual retinal vascular layers in high resolution. On this slide are examples of the different stages of non-proliferative diabetic retinopathy, NPDR. As we can see, the retinal vessel change as the severity of NPDR increases. Currently, in the clinical setting, artery vein differentiation is not available. In our lab's research, we can utilize the spectral information such as the light information in fundus photography on the top and OCT on the bottom to differentiate vessels as arteries and veins. Fundus photography can be useful. However, fundus images cannot provide high resolution of individual retinal vasculature. Furthermore, fundus photography guided AV classification in OCTA requires 2 imaging modalities, a fundus camera and an OCT machine. This is not visible. Whereas OCT can provide both high resolution and separation of individual retinal layers. Furthermore, OCT and OCTA are from the same imaging modality. Therefore, OCT-guided AV differentiation in OCTA can hold promise for easy use in a clinical setting. Using OCT, we can derive various features for AV differentiation. In the top panel, from the en-face projection, in the lateral direction, we explored several features such as the ratio of the vessel width to the central reflex, the average profile brightness. We explored these features in order to differentiate artery and vein. In the bottom panel, we recently demonstrated that the depth-wise features in the axial direction can be used to differentiate arteries and veins. And now, using these features, we can employ a machine learning algorithm to classify vessels as arteries and veins. Here, we show an example of OCT features to guide AV classification in OCTA. And using the EnFast OCT, we first classify each vessels as artery and vein. And since OCT and OCTA are from the same modality, no image registration is required. Therefore, we can guide the information from the OCT into the OCTA by simply overlaying the OCT AV map onto the OCTA. We can employ vessel tracking to generate a high-detailed vascular map. Based on our previous study, both OCT and OCTA was required to produce a detailed vascular map. We therefore use them as inputs in a deep learning model for automated AV classification in OCTA. The output of the CNN is an RGB image where the red channel is artery and the blue channel is vein. In our study, we reviewed 86.71 and 86.80% accuracy for arteries and veins respectively. In a follow-up study, we wanted to investigate the different types of image inputs, OCT and OCTA, on AV classification, as well as the different fusion operations, the early and late fusion. The OCT only architecture had the worst performance of the three. However, that is expected as the OCT has less vessel contrast. Therefore, the CNN cannot predict the AV map in high detail. The OCT-only architecture has comparable performance to the early and late fusion architecture, with the early fusion having slightly worse performance and the late fusion having slightly better performance compared to the OCTA-only architecture. To understand the deep learning results, we employed the use of saliency maps to show which pixels are important for segmentation. The figure on the left shows the saliency map for a single pixel, and the figure on the right shows the saliency map for a vessel segment. And based on the saliency maps, it suggests that for the OCTA-only architecture, the CNN uses a localized region, both inside and outside the vessel. The highlighted area inside the vessel suggests features such as the vessel texture and size contributes to the classification, whereas for the area outside the vessel suggests that the capillary free zone contributes to the classification. The saliency map for the OCT shows a much larger area is used for classification. This is most likely due to the lower vessel contrast in OCT. Therefore, the CNN needs this information for prediction. In our recent study, we have explored the use of differential AV analysis for quantitative OCTA features. But different retinopathies may affect the capillaries first. Therefore, AV segmentation at the capillary level resolution may be important for clinical diagnosis. Based on our recent study, we also demonstrate the ability to use deep learning to review capillaries using OCTA. We can achieve this possibly due to the previous saliency map analysis that we carried out. And using OCTA, there are several potential features that the CNN can leverage for AV segmentation. We have also employed the use of differential AV analysis for quantitative OCTA features for disease staging. On the left figure, we analyzed the blood vessel caliber and tortuosity. We showed that for the vessel caliber, if we measure the mean vessel caliber, there is little difference between the stages of NPDR. However, if we separate the arteries and veins, we can see that there is a polarizing trend. The arteries constrict as the stage of the DR progresses, whereas the veins dilate with disease progression. Now, taking the ratio of the artery and vein vessel caliber increased the ability to differentiate arteries and veins. We performed a similar analysis for sickle cell retinopathy, and in this study, we reviewed that most of the changes in SCR occur in the vein. In summary, we demonstrated light oximetry in color fundus and spectral OCT to guide AV classification, and we explored OCT geometric feature-based machine learning. We also developed deep learning for automated AV classification and showed the optimal AV detection using deep learning fusion strategies. And finally, we demonstrated that deep learning AV segmentation is visible at the capillary level. Thank you very much for listening.
Thank you, David, for that really interesting talk about differentiating vessel types on OCTA. Up next will be Fatala Ben-Mansour from Roche, speaking about moderately severe and severe NPDR identified by deep learning. Fatala.
Thanks, Professor Lang. So hello, everyone. I would like to thank the organizers for the opportunity to present our work here. So I'm a clinical imaging data scientist working for Roche, and it's my pleasure to present our work. So the results were, next slide. Yeah. The results we're presenting today are the fruits of an industry academia collaboration between our group and IBLI, the Association of Innovation and Biomedical Research on Light and Imaging in Portugal. And I would like to truly thank all our collaborators, especially from the academic side, and particularly to Professor Kunavas for his guidance. These are the financial disclosures of all the co-authors. The audience is very familiar with diabetic retinopathy, but I will give a bit of context. So the global prevalence of diabetic retinopathy is projected to increase from over 400 million in 2017 for diabetes. Global prevalence of diabetes is projected to increase from over 400 million in 2017 to over 600 million in 2045. And diabetic retinopathy is the most frequent microvascular complication of diabetes, affecting approximately 1/3 of adults over 40 years old with diabetes. It's a leading cause of vision loss for working age adults. So the gold standard for scoring DR severity is the ETDRS DR severity scale, as shown in this slide. And progression on this scale is linked to development of vision-threatening conditions. However, the scoring, as highlighted in the previous presentation, specifically on the previous session by the Wisconsin Reading Center, Dr. Damalpali, well, the grading is based on 7 fields stereoscopy, and it's not carried over in clinical practice. DRSS is used in clinical trials rather. And actually, the question is whether artificial intelligence or AI can help in facilitating the identification of relevant patients. So we're focusing on 4753 DR severity scale. Those are moderately severe to severe NPDR, because these patients are at high risk of progression to VTDR, as shown in the early treatment diabetic retinopathy study or in other more recent studies. And actually, as also mentioned in the previous session, 4753 is one of the key eligibility criteria for DR clinical trials. So our objective is to develop an AI model to identify moderately severe to severe NPDR from color fundus photos. And we previously developed such DL models, and actually we reported the results at last year's Ophthalmology AI Summit. So this year, actually, thanks to the academic collaboration we had, we are able to report results of the trained model on an independent cohort from a different country. So the DL models we developed were based on a large cohort of diabetes patients from the United States. And we had, through the academic collaboration, the opportunity to evaluate the performance of this model on a cohort of patients from a different country. So let me give some context about the used cohorts for the development and for the evaluation, as well as the methodology. So the used cohort was, our development data set consisted of ETDRS graded color photos from eyes of over 37,000 patients with diabetes. And the images were acquired with the Zeiss instrument. DR severity was in presence of diabetic macular edema were assessed from 7 fields correspondence photos by professional graders at a centralized reading center in the US. And in this large diabetes cohort, the prevalence of 4753s was 2.2%, as highlighted in this graph. So with this data set, we trained an Inception V3 model, rather standard model with transfer learning to classify eyes of whether being in this category or not. So basically, the task of the model is to identify these 2.2% of the eyes. Now, regarding the independent evaluation data set or cohort, this consisted of patients enrolled in a natural history DR progression study, which enrolled patients from Portugal mainly, and followed them over 5 years on a yearly basis. So 172 patients completed the study, and the image data was acquired with a different instrument, a Topcon instrument. And images were graded at the Coimbra Ophthalmology Reading Center in Portugal. So at the baseline visit, as you can see, most of the patients had mild diabetic retinopathy, and a few progressed over time on the DR severity scale. So overall, we had imaging data from 635 unique eyes visits with valid DR severity scale, which we used to evaluate our algorithm. And on these, of these eyes, 14 had the relevant severity scale, that is 4752. Methods-wise, we follow the standard approach, splitting the development data set into a training, a tune, and a test set. Basically, we leveraged all the 7 fields. We had a very systematic approach, model trained at the image level. And we leveraged our tuning sets to optimize on architecture. So I mentioned Inception V3, but we tried all different architectures, and the difference in performance was really minor. We also optimized for model hyperparameters, such as dropout rate, number of training epochs, and the like. So we also use a tuning set to stabilize the operating point of our model. So to have a systematic way of estimating the model performances on the test set and on the independent evaluation data set. And the performance was evaluated in terms of AUC, specificity, and sensitivity. So next I'll be showing the results. This slide are the results on the test set of the development cohort, the US cohort. Very good performances, despite the low prevalence of the specific disease stage we've been looking at. So 0.98 AUC, sensitivity of 97%, and specificity of 92%. But when going to external dependent cohort, we observed a drop of performance, not dramatic though. So we had an AUC of about 92, a sensitivity of 1, meaning that we had 0 false negative cases, which is very important for such a low prevalent subpopulation. And we had a specificity of 68.9%. So as you can see from this plot, the operating point, that's the red point highlighted on this plot, wasn't optimized for the specific set. Again, I'm just repeating myself. This point, or the operating point, was decided based on the tuning set of the development data. So to conclude, despite differences between the development and the evaluation data set in terms of patient population, used imaging instruments, the model rendered good performance and generalizability for identifying eyes with DR severity scale between 47 and 53. And eventually, with additional validation on more diverse data sets, this model could be used to inform screening of patients at high risk of progression to vision-threatening conditions. So basically, such an algorithm could play an important role in screening strategies for DR preventive trials. With that, I would like to thank the organizers again. I'm looking forward to your questions.
Thank you so much for your talk. As a reminder to our audience, please feel free to enter questions in the box below your screen. Our next talk will be from Daniel Padilla on automated etiologic classification of macular edema in OCT scans. Daniel.
Thank you so much, and hello everyone. I'm so excited to be here with you. I greet you from Bogota, Colombia, and my title today is Automated Etiologic Classification of Macular Edema in OCT scans. I have no financial disclosures for this presentation. I would like to start by expressing my special thanks to the members of the MyLab Research Group and the Departments of Ophthalmology and Computing Systems of Universidad Nacional de Colombia. Let's start with some facts. There is an outward trend in population aging and consequently an increase in the global burden of chronic diseases. Nowadays, there are more than 250 people with blindness and severe visual impairment, and this number is projected to double by 2040. The neovascular, age-related macular degeneration, diabetic macular edema, and retinal vein occlusion are the three main exudative macular diseases, and these are the most prevalent and potentially blinding in older patients due to their structural and functional sequelae. OCT is the gold standard test for evaluation of macular edema by the proper recognition of location, extension, and some specific patterns or characteristics that are known as biomarkers that could be evaluated as indicators with diagnostic and predictive values. So, for example, we have some important biomarkers, for example, in AMD, like drusen, subretinal fluid, hyperreflective foci and tissue and PET. In the case of diabetic macular edema, for example, with DRI, hyperreflective foci, and the case of cysts. And in the case of retinal vein occlusion with macrocysts, hyperreflective foci, and subretinal fluid. So we know that there is an increase in the incidence of these diseases. It increases also the number of tests. And there is not such a large number of ophthalmologists or expert evaluators in order to analyze them. And there is also a shortness of ophthalmologists in our developing countries. As we can see, the age in the population grows faster than the profession. Nowadays, the diagnosis still relies on the manual evaluation performed by the expert evaluators, which is a subjective, challenging, and time-consuming process. And here's where artificial intelligence can arise to overcome these needs in order to provide the advantage of having a lot of information of data in a very short time. We know there is a pivotal study that conducted the first FDA-approved artificial intelligence-based algorithm for diabetic retinopathy with the superiority endpoints with specificity and sensitivity higher than 85%. And this serves as a reference in order to compare the performance of the models with an expert ophthalmologist. So it was our purpose to develop a deep learning approach in order to identify macular edema and classify its cause between the three major retinal exudative diseases. So the scans were obtained from data repositories from ophthalmology clinic and in open access databases, and they were annotated with 4 key biomarkers that were fluid, including intraretinal and subretinal fluid, as well as cysts, including macro cysts, and in fact, in the way of hyperreflective foci and tissue and drusen, and labeled as control or disease. These images were split into the training, validation, and control sets, including the 70, 20, and 10% of the images, respectively. So our model was developed by following 4 consecutive phases. The first one was the segmentation of biomarkers. It was a process that included the manual segmentation by the 2 expert ophthalmologists, and of course the training of the model in order to recognize, identify the proper biomarkers by the use of convolutional neural networks like SEUnet, Pix2Pix, and DREW. Dice coefficient was used to evaluate the performance of biomarker segmentation by analyzing these methods as a coincidence between the manual segmentation and model prediction. As we know, this Dice coefficient goes from 0 to 1, where 1 is the perfect agreement. And for the purpose of biomarker segmentation, we reach or we target a value higher than 0.5. The next phase was the combination of biomarkers in a single image. As we have previously discussed, the importance of the association of biomarkers in order to determine the underlying pathology. This was made to achieve binary classification for each disease, which means the design of 3 separated architectures for analyzing one single scan and recognize the presence of or absence of each disease in every single scan. And of course, the multi-class classification approach that joined the previous separated architectures in order to classify these images. This was done through a regression, an operation of multiple logistic regression by the softmax activation function. The performance metrics were accuracy, sensitivity, and specificity in order to evaluate the binary and the multi-class classifications. So what about the results? This table shows the DICE coefficients for biomarker segmentation. And as we can see, the best performance was achieved by ResUnet and SEDU convolutional neural networks. Here are some examples for these identifications. For example, in subretinal fluid, the first row shows the original image, the second, the manual segmentation conducted by the expert ophthalmologist, and the third and fourth, the model predictions by ResUnet and SEUnet, as we have analyzed as the best convolutional neural networks for the identification of biomarkers. Here's the case of cysts, of drusen, and the case of hyperreflective foci and tissue. It achieved a good performance in order to make the binary classification, as we can see. And for this first approach, the best results were for the identification of diabetic macular edema. But the joining through the softmax function activation led us this confusion matrix and this final performance metrics. And as we know, these were the best results in order to classify neovascular age-related macular degeneration, followed by diabetic macular edema, contour images, and finally retinal vein occlusion with a good accuracy, sensitivity, and a lower specificity because of the challenge of that could offers the differentiation between a macular edema from retinal vein occlusion from other causes like diabetic retinal edema. But the global performance was so strong, as we can see in these records with the area under the curve, with values higher than 97% for all diseases. In order to achieve visual explanation and behavior of the recognition and the combination of these biomarkers, we explore the GradCam exploration in order to make, for example, this recognition of subretinal fluid and hyperreflective foci and drusen for NMD. In the case of intraretinal fluid, DRIL and hyperreflective foci for diabetic macular edema, and macrocysts and hyperreflective foci and subretinal fluid in the case of retinal vein occlusion. In the absence of biomarkers and fluid in the case of normal images. So our deep learning approach gave us a good way in order to identify macular edema and the classification of its causes. And it could optimize the efficiency and timeliness of appropriate etiological diagnosis of macular edema and improve patient access and clinical decision-making, useful in places with a shortage of specialists like our developing countries and for readers that evaluate OCT scans remotely. Of course, other clinical features for diagnosis, treatment, and prognosis should be included, including larger data sets of technology centers and expert readers. And this could be an interesting teaching tool for reading and interpretation of OCT and incorporated into digital health strategies like telemedicine in light of challenging situations like the recent COVID pandemic. Thank you very much.
Thank you, Daniel, for that really important talk about detecting fluid in these macular diseases. Our next talk will be from Alvin Liu from Johns Hopkins, looking for predictors for 9 diagnostic images in a real-world deployment of AI in DR screening. Alvin.
Hello, everyone. My name is Alvin Liu. I'm a retina specialist from Johns Hopkins. I would like to thank the organizers for having me speak today. I do not have any financial disclosures. Today for my talk, I would like to share our experience in deploying AI-assisted diabetic retinopathy screening in the primary care setting at Johns Hopkins, and specifically our experience in dealing with non-diagnostic images. Let me start with some background information. The system that we deployed at Johns Hopkins is the IDX DR system developed by Digital Diagnostics. It is the first FDA-approved, fully autonomous AI system in any medical field. Overall speaking, the algorithm has several components to it. First, it is meant to be used in a primary care setting using the Topcon NW400 camera. And for each eye, 2 images are first taken, a color fundus photograph centered on the macula and centered on the disc. Before it can make a diagnosis or classification, the first step of the algorithm will decide whether the images are gradable or not. And the algorithm will only proceed to the next part if the images are indeed gradable. Then the algorithm will decide whether referable diabetic retinopathy, defined as more than mild diabetic retinopathy, is present or not. We deployed this system at 4 different primary care clinics. These are outpatient-based, community-based primary care clinics, so not situated in a big hospital. When we first decided to deploy the system, one of the biggest questions that we had in mind and the clinics had in mind was whether the patients should be dilated or not. Overall speaking, our primary care colleagues were quite reluctant in dilating the patients because they are not very comfortable with giving eye drops, and also they were worried that patients would be turned off by the screening program if they were told that they would be dilated. So in order to answer that question, we referred to existing literature at that time. We looked at the pivotal clinical trial that led to approval of this technology. In that clinical trial, 76% of patients had gradable images without any dilation. There was also another pilot study done in Poland using the same system, showing that 78% of patients did not need to be dilated to get a gradable images. Based on these numbers, we thought that these were acceptable numbers, so we did not have a dilation protocol in place. So we ran the program for a few months, and to our surprise, we had a very low diagnostic rate of only 49%. We suspected that such a low diagnostic rate was due to the fact that these patients were not dilated. And to adjust for that, we started dilating patients after they failed those first screening tests. And our diagnostic rate did improve from 49 to 79%. Despite this is still not an optimal and desirable workflow, because what that means is that we only dilate the patients after they fail the first screening. And this in turn did add quite a bit of screening time and inconvenience for the clinic workflow. That's why the goal of this study was to look back at the data to identify risk factors for non-diagnostic exam. And the point is to selectively dilate these patients prior to the AI-based screening so that we don't have to repeat the testing. This was a retrospective case control study looking at data from August 2020 and May 2021. In terms of data collection, we first did a literature review to identify risk factors that have been associated with either poor dilation or poor retinal imaging quality. And the ones that we looked at include age, BMI, type of diabetes, race, ethnicity, A1C, hypertension, and smoking status. In terms of our statistical methods, we looked at the data in two major different ways. First, we did an exploratory mixed effects model. Second, we built a predictive model using multivariable logistic regression. Here's a table showing the baseline demographics of our patient cohort. In total, we included 241 patients. As mentioned, we had a low diagnostic rate of 49% without any dilation. Of note, within our cohort, these patients were recruited mainly in the Baltimore County area, and we have a relatively high percentage of African-American patients at 55%. In terms of factors that were statistically different between a diagnostic and non-diagnostic group. The ones that we found included age, BMI, smoking status, and type of diabetes. Next, we did modeling using mixed effects model with the location as the random effects, given that this program was implemented at 4 different sites. These are the variables that we found were associated with non-diagnostic exam. The type of diabetes, specifically type 1 diabetes, smoking status, older age. 3 other variables were borderline statistically significant, including a non-white race, male sex, and the presence of hypertension. Next, we looked at the data a little bit differently using multivariable logistic regression. The same variables came out to be associated with non-diagnostic exam. The only difference is that when we looked at non-white race, male sex, and hypertension in this particular model, they were actually statistically significant. Next, using the multivariable logistic regression model, we split our data into 5 different folds and did a 5-fold cross-validation to see how good our model was in terms of predicting which patients would be non-diagnostic. After a 5-fold cross-validation, we got a reasonable result of an AUC of 0.757. Of note, with our method, we could also adjust the different prediction cutoff value in order to achieve a different combination of desirable sensitivity and specificity. So as a conclusion, in our real-world deployment of AI-assisted diabetic retinopathy screening, we found a significant difference in the diagnostic rate without dilation between what was found in a clinical trial and in our experience. When we looked at real-world deployment specifically, there is also variability, considering that in Poland, that study used the same system. They had a 78% diagnostic rate without dilation versus 49% in our study. we think the main reason to explain these differences was the patient composition in our cohort, specifically race. As a comparison, in the pivotal clinical trial, 63% of the patients were Caucasian compared to 36% in our cohort. On the flip side, in the pivotal clinical trial, 28% of the patients were African American versus 55% in our cohort. We believe that given the higher percentage of African American patients in our patient population, these patients tend to not dilate as well in dim light environments or without pharmacological dilation, which in turn led to worse image quality, which in turn led to a higher non-diagnostic rate. There were several other risk factors that we thought could be related, although we were not able to verify independently. For example, in the pivotal clinical trial, 89% of patients were either pseudophakic or did not have any visually significant cataracts. We think that it's possible in our patient cohort, as compared to the pivotal clinical trial, our patients had a higher percentage of visually significant cataracts or higher percentage of hypertension or higher percentage of smokers. As the next step, we plan to perform a prospective study with 2 arms. In the first arm, we will integrate our predictive model into EPIC as a calculator and prophylactically dilate patients, which the model predicts will have a high chance of having non-diagnostic images. And in the second arm, the clinics will have the standard care of dilation, and these patients will only be dilated if they fail the first round of screening. We predict that in the arm with the predictive model, the overall visit time should be shorter, and the overall diagnostic rate may also be higher, given that in our experience, some patients simply refuse to be dilated after they failed the initial screening, given the inconvenience and time involved. And that's all I have. I'd like to thank the organizers again and my collaborators here. Thank you.
Thank you so much, Dr. Liu, for this great talk. I really love these real-world implementations of AI and seeing how it all plays out. And that's really what we're trying to focus on here in this meeting. Next up is Yasha Modi from NYU, who will be speaking about vein occlusion and the response to aflibercept using machine learning models. Yasha.
Great, thank you so much, Ted, and thank you to you, Dr. Lim, Dr. Singh, all for putting together just an amazing meeting. I've learned so much today, and as a clinical dummy, I think this has been hugely informative to me. So we're going to be talking a little bit about predicting outcomes and treatment frequencies following monthly intravitreal aflibercept for macular edema secondary to central retinal vein occlusion. This was a joint project that Dr. Singh, Dr. Mehta, and I did with the research team at Regeneron, and here are disclosures. And in order, the data set that we use comes from the Copernicus and Galileo study. And this was the registration clinical trials that approved aflibercept for the treatment of macular edema secondary to central retinal vein occlusion. And in the design of the study, which is relevant, the patients received monthly aflibercept injections for the first 6 months, or they received sham injections. But at week 24, all patients then transitioned over to a PRN basis. And then they were followed out to either 76 or 100 weeks. And so the PRN retreatment criteria for this is sort of exactly what we would imagine in clinic: those that had an increase in the central subretinal thickness, those with new amounts of fluid, both intraretinal or subretinal fluid, or deviations in visual acuity, either a gain or loss of 5 letters between a visit. And not surprisingly, when we switch over to PRN treatments, we've had a slight degradation of the vision, and then there's variation in the central subfield thickness changes. So there we lose that sort of predictable stability that we see, where we have this beautiful visual acuity stability and central subfield thickness stability. So then the question is, can we build a model then to understand what will happen when we switch from this monthly therapy to PRN dosing? And so essentially what we did was we used the Copernicus and Galileo data, and the goal was to develop a machine learning model to predict absolute best corrected visual acuity and change in best corrected visual acuity at weeks 52, to evaluate for change in central subfield thickness at week 52 relative to week 24, and then to see if we can predict the number of injections required at that PRN arm from weeks 24 to weeks 52. Now, remember, we're only using one small data set. We're using the registration clinical trials of Copernicus and Galileo. So the statistical model that we used was a random forest model to develop this machine learning model. And this is sort of something that we've seen throughout the day today, except with a lower number of data patients, where we have the data input from the registration clinical trial. 80% of that went to develop the sort of model in which this random forest model ultimately builds these multiple decision trees and then merges them together to establish a more accurate and stable prediction. And once we have that predictive outcome, that can then be tested in 20% of the data, which we can then use to determine the performance. And that could be measured by a correlation coefficient or an area under the curve, depending on whether or not we have a continuous or categorical variable. And because we didn't want to make any assumptions, and we were also using a small number of patients, we inputted a lot of data, both baseline demographics and disease characteristics that are shown here, and then a host of baseline laboratory evaluations that are acquired at the time of the registration clinical trial, and then post-baseline visual acuity at various time points, central subfield thickness at various time points, and then the NEI-VFQ scores at week 24 to kind of make all the predictive values for the model. And so when we look at the results in terms of predicting visual outcomes at week 52, what we see is on the x-axis, this is the observed absolute best corrected visual acuity. And then on the y-axis, we have the predicted absolute best corrected visual acuity. And so this model with very reasonable accuracy was able to predict the absolute best corrected visual acuity. And some of the things that were noteworthy, some of the key predictive factors were best corrected visual acuity at week 16, 20, and 24. So basically the vision that you have when you switch over from monthly treatment to PRN treatment was most predictive in understanding how they're likely to do at the conclusion at week 52. Now, when we look at change in central subfield or change in best corrected visual acuity, this model is slightly less predictive here, but we see similar predictive factors. We see that the best corrected visual acuity at week 20 and week 24 remain highly predictive. And now we're seeing actually that the best corrected visual acuity at baseline is predictive. So that's looking at both absolute and change in best corrected visual acuity. And then we're moving on to understanding anatomic outcomes at week 52. So when we look at absolute central subfield thickness, the model is not able to predict in any way what the absolute central subfield thickness would be. So here we have observed absolute central subfield thickness on the x-axis, and then predicted absolute central subfield thickness on the y-axis. And again, in terms of its predictive factors, it doesn't really yield anything very meaningful either clinically or by the model. However, kind of interestingly, when we look at the change in central subfield thickness, there's a better predictive value. And again, we're sort of seeing these recurring themes of best corrected visual acuity being predictive, as well as now the central subfield thickness at baseline being predictive in these scenarios. So, one of the questions that a lot of clinicians have is, if we switch somebody over from a mandated monthly treatment strategy and we're going to a PRN treatment, how often are they going to need to have retreatments, and what's that likelihood of? Are we able to predict that with any meaningful accuracy? So we asked the question, could we predict patients who are going to receive 2 or less aflibercept doses after switching over to the PRN arm? And what we realized is that with some modest accuracy, we were able to predict those who would receive 2 or less relative to those who are going to receive more. And some of the meaningful drivers of this was the central subfield thickness at baseline and at week 4. So this is sort of a proof of concept that we can use small data sets in a rigorous fashion to obtain some predictive value in terms of understanding visual outcomes, changes in macular thickness, and dosing frequency. Now, certainly this is a small data set and it needs to be validated on much larger data sets. But what we've learned in this short time is that patients with higher central subfield thickness at baseline in week 4 were more likely to receive 2 or more PRN treatments after switching over from fixed dosing. And so this is sort of a proof of concept that we're hopefully taking to the next step where we can test this on larger data sets of patients. Thank you.
Thank you so much for that talk, Yasha. I look forward to chatting more about that during the discussion section. Up next will be Aiden Puccio, who will be speaking about the role of AI in the analysis of fluid biomarkers for the diagnosis and management of glaucoma. And we're going to be shifting into the glaucoma for the next few talks, and excited to move the discussion away from the retina for a little bit. Thanks.
All right. Hi, everybody. My name is Aiden Puccio. I'm a third-year medical student at Queen's University in Kingston, Ontario. Thanks very much for having me today. I'm really happy to present my project, the role of artificial intelligence in analysis of biofluid markers for diagnosis and management of glaucoma. It's a systematic review. Before we begin, I'd just like to thank my supervisor, Dr. Tina Felfelli, really fantastic mentor and researcher, and thank the organizers as well. So, glaucoma is the leading cause of irreversible blindness worldwide, with a projected global prevalence of almost 112 million by 2040. So with the growing burden of disease, accurate and timely solutions to address disparities in screening, diagnosis, and management are really critical. Molecular etiologies have been implicated in glaucoma, such as cytokine and immunologic dysregulation, lipid metabolism abnormalities, lysosomal action, angiogenesis, an array of metabolic syndromes. But there hasn't really been a definitive sort of characteristic biomarker or pathogenic mechanism in glaucoma identified. These biomarkers are often contained in biofluids such as serum, tears, and aqueous and vitreous humor, which is relevant because particularly in ophthalmology and in glaucoma, these patients are often in the clinic quite frequently, have multiple surgeries. So accessing these biofluids is maybe more viable than it might be in other diseases. So these biofluid markers represent massive, highly dimensional data sets, which I think traditional statistical methods and analytic methods struggle to analyze, which is where AI really comes in. So AI is really well suited to analyzing these large data sets. It's important to note that AI already has sort of robust and varied applications in glaucoma care. A lot of imaging-based AI tools, a lot of the previous presentations really fantastic, very analogous to what you see in glaucoma. So, analysis of OCT or fundus photos to diagnose or glaucoma or predict prognosis. But it's also important to say that there's different AI tools that are suited for different roles. I won't get into the weeds here because I'm sure many of you are already very familiar, but supervised AI techniques such as artificial neural networks or discriminant analysis are trained using defined cases and can learn to classify or predict outcomes. While in contrast, unsupervised AI, including cluster analysis or principal component analysis, are adept at determining trends in highly dimensional data sets and can group unlabeled data using similarities or differences to find associations in large data sets. And finally, bioinformatics are really fantastic at translating complex findings into interpretable information. So clinical tools using AI analysis of biofluid markers could have diverse applications in glaucoma. So for example, automated glaucoma screening is sort of one area, and also pathogenic exploration, because there really isn't a clear pathogenic mechanism in glaucoma. So we did a systematic review, 5 databases, sort of title screen to abstract screen to full text screen to appraisal and extraction, very standard systematic review methodology. We screened about 10,000 abstracts and then 1,000 full texts, and finally included 39 papers. Our inclusion criteria were original peer-reviewed studies that analyzed biomarker concentrations to predict or modify patient therapy outcome or diagnosis in glaucoma. These studies had to use AI or bioinformatic analysis. They had to analyze protein, lipid, or metabolite samples from vitreous fluid, aqueous fluid, tears, or blood products such as serum, plasma. And finally, studies using regression analysis, which is sort of the simplest form of AI, had to either be longitudinal or apply their findings directly to change the treatment or predict prognosis in study populations. Our exclusion criteria were articles studying ophthalmic diseases that only affect pediatric patients, such as retinopathy of prematurity, studies using non-human subjects, studies exclusively using post-mortem samples from eyes, non-English studies, and then finally abstracts, reviews, systematic reviews, and meta-analyses. So of our 39 papers included, the majority of them were cross-sectional papers, 23, followed by prospective cohort studies and retrospective cohort studies. We sort of classified the papers based on their objectives. So the identifying characteristics papers explored biomarkers with the intention of exploring pathogenic mechanisms of glaucoma. Studies classified under diagnostic clarification sought to identify biomarkers that could really develop an accurate predictive model. And finally, the treatment decision papers, classification of biomarkers were used to guide selection of treatment options or predict outcomes following treatments. So again, the majority of papers here focused on primary open-angle glaucoma, followed by primary angle closure glaucoma. And in terms of the biofluids that were analyzed, the majority were looking at blood products in serum and plasma, followed by aqueous humor. This makes sense because, you know, obviously blood is probably the most widely accessible biofluid in medicine at large. And so a lot of these studies sort of, we're getting blood samples, you know, previous to enrollment. So, and aqueous is probably the most accessible intraocular fluid. So I'd like to shift and talk about sort of studies that were looking to identify characteristic biomarkers. So these were studies that were looking to find a biomarker that was either, you know, significantly increased or decreased in glaucoma patients versus control. The objective of these studies sort of varied depending on the papers. You know, some were trying to find one just with the intention of finding sort of a characteristic biomarker and developing treatments. Some were trying to develop, you know, diagnostic models. But regardless, these papers were just looking at differentially expressed biofluid markers. So studies examined between 1 and 773 biomarkers. In primary open-angle glaucoma, 175 unique differentially expressed biomarkers were identified, and over 75 pathways were identified to be significant. Glutamine was the most commonly, you know, significant individual biomarker, which was found to be significant in 3 papers. And the glycolytic, inflammatory, and autoimmune pathways were the most commonly variable pathways in primary open-angle glaucoma. Now, you might know, like, 3 papers for this biomarker, 3 papers for these pathways. That's a very, very low amount of agreeability between papers, given there was 23 papers looking at primary open-angle glaucoma. So, you know, not a lot of agreement about what biomarkers were significantly different in glaucoma patients. In neovascular glaucoma, hemoglobin A1C and VEGF were both implicated in neovascular glaucoma development. These were both implicated by 4 papers, but there were significantly conflicting findings. Again, about 4 papers found each of these biomarkers to be insignificant. And then for both pseudoexfoliation glaucoma and angle closure glaucoma, 20 biomarkers were identified over a number of studies, but none of them were confirmed by more than 1 study. So in terms of predictive accuracy of the models developed, so first I want to just point out that, you know, globally these models were used to distinguish between you know, glaucoma and controls. And they kind of globally are quite accurate. Like, you know, most of them have accuracies or area under receiver operator curves or sensitivity or specificity above 80%. So quite strong overall. But more specifically, I want to point out that the artificial neural network papers and the discriminant analysis papers were quite fantastic, very, very accurate. And then finally, so I sort of talked about on the previous slide how there wasn't really a defining characteristic biomarker. Each of these models sort of used entirely different biomarkers to develop their predictive models. And biomarker selection did influence accuracy. So in this 11th model here, their accuracy range from 0.57, that's using 1 biomarker, to you know, 0.87 using a different one. So biomarker selection did affect model accuracy. And then finally, for risk of bias, I won't get into the details here, but the areas of bias in the studies we included that I want to point out were non-significant findings were often omitted. You see this a lot in AI papers, especially using unsupervised AI, where if you're looking at 700 biomarkers, obviously you can't report all the insignificant ones, but it does lead to some reporting bias. Additionally, cross-sectional studies inconsistently reported the inclusion criteria of participants and didn't really describe their study population in great detail. While a lot of the cohort studies didn't describe loss to follow-up or describe strategies to mitigate incomplete follow-up. Finally, a lot of the papers using complex AI, so supervised AI, unsupervised AI, and bioinformatics, they very rarely explain the rationale for AI selection or the algorithm activities. Anyway, I see my time is up. But yeah, thanks very much for having me.
Thank you so much for your talk. And great to see AI being employed on other things besides images. Up next will be Sally Baxter from UC San Diego, talking about modeling of glaucoma using the All of Us research program from the NEI. Sally.
All right, thank you so much for having me. I'm really thrilled to be joining this great group of speakers and talking a bit about our work doing predictive modeling in AI to look at glaucoma progression using electronic health record data from the All of Us research program. I don't have any commercial relationships to disclose, a couple grants that are listed there. And just to set the stage a little bit, we all know that glaucoma is the world's leading cause of irreversible blindness. And while there's a lot of interest in looking at fields and OCT and now OCTA, I became very interested in understanding the role of systemic disease and how we might be able to look at that with electronic health record data. And so the digitization of healthcare data, especially over the last decade or so, has really opened up new opportunities for understanding these relationships, particularly vascular risk factors like hypertension and cardiac disease. And so our question was whether data-driven modeling of systemic attributes obtained from existing EHR data would predict the risk of glaucoma progression. And my apologies, so the animations were a little bit, I should have modified those before the presentation. But essentially, this idea of how does vascular regulation in the body affect progression of glaucoma based on this sort of vascular hypothesis and optic nerve perfusion pathophysiological framework? And so to do that, we wanted to use a newer data source, which is called the All of Us database. And when I first started using this, it was a very new resource. They started the program in around 2016, so it's only been around for a few years, and they're really gaining traction in enrollment. And I think it's a great opportunity for ophthalmology researchers. And part of my goal in talking about it is to encourage more members of the ophthalmic research community to utilize this great resource. So it's a nationwide prospective cohort study aiming to enroll 1 million people in the United States. They have a specific emphasis on diverse enrollment and reaching out to individuals who come from populations who have been historically underrepresented in biomedical research. There's a wide range of data, including survey data, electronic health record data, physical measurements, wearables like Fitbit devices, and biospecimens, so blood and urine. And now that's opened up a whole new avenue with the recent provision of genomic data as part of the database. So just a visual infographic kind of summarizing the scope of enrollment right now. They're about halfway to their enrollment goal with almost 500,000 participants right now who have at least started signing up. And then the initial steps of the program have been covered by a third of their enrollment goal, so 341,000. Over 300,000 individuals in the program have consented to sharing their EHR data, and over 365,000 have provided biosamples. I think this part and the bottom right here is kind of the most impressive portion, is that over half of the individuals in the cohort come from racial and ethnic minorities. And if you look at a broader definition of diversity, that includes, socioeconomic diversity and education, individuals with disability and so forth, then over 80% of the individuals in this database are from populations who've been historically underrepresented in biomedical research. And I think this came up in Alvin's talk about, the role of race and looking at diverse populations. So this is a really unique resource to be able to look at health outcomes and pathophysiology and a whole host of questions in people who have not been traditionally well represented in clinical trials and clinical research in the past. So what we did in this study was that we started with a predictive model that I had developed using data from UC San Diego. And one of our goals was to use all of us to try to externally validate our prior single center model. Then we wanted to develop new models trained with data from all of us and compare its performance to see whether it would perform better than our original model. And then, of course, we wanted to share insights from our experience using the database and the cloud-based researcher workbench tool, which is a platform for researchers who want to work with this database with other ophthalmologists and vision scientists to share it with the rest of the research community. So in this initial demonstration project, this was kind of near the start of when they were making the data available. So there were a lot fewer participants at that time, but we used SNOMED codes to identify people with primary open-angle glaucoma. And our definition of glaucoma progression, which is a little bit of a limitation of this database, was actually based on need for surgery. So we use CPT codes for surgery. Unfortunately, the database does not include imaging such as OCT. It does not include visual fields. So we weren't able to use some of those metrics to define glaucoma progression. So our study cohort, as I mentioned, were adults with primary open-angle glaucoma. And this is a screenshot from the All of Us researcher workbench. And you can see that there's a pretty easy to use user interface that lets you clearly define inclusion criteria and exclusion criteria. You can indicate specific diagnosis codes. You can use lab values. You can include temporal criteria like this criteria 6 months before that one. And then what the workbench will do is give you a preview and tell you how many people in the database meet the criteria that you have designated, and also what their demographic breakdown looks like. And you can see here in the dashed lines, I've just kind of X'd out the non-binary gender identity because we're not allowed to show data where the group is less than 20 participants. But it's a very easy to use user interface, and what it'll do is generate a structured query language or SQL query that will then extract that cohort of patients from the database and launch it into your notebook when you're ready for analysis. So for the variables, as I mentioned, we use glaucoma surgical intervention based on CPT codes to be a proxy for progression, and included a wide range of predictor variables like vital signs, physical measurements, comorbid conditions, and medications. And again, for all of those, you can build those in the workbench. And here's a screenshot, where we were looking at blood pressure metrics. And had put in, various LOINC codes, which are kind of standard structured observations for clinical data. And so you can very easily designate the variables you're interested in looking at. And then when you do the analysis, essentially you can designate your cohort, extract the data on the variables you're interested in, and then spin it up and analyze it in a Jupyter Notebook environment. They have notebooks in R as well as in Python, so there's some flexibility depending on what your teams typically use. And in this case, we train models using logistic regression, random forest, and artificial neural networks. So you can see in terms of the general cohort characteristics, the All of Us cohort, and again, this is a few years ago, so the number of patients has increased since then. But even then, it was over triple the size of our single center cohort. We had much better representation of Black or African American individuals, which, as everyone knows, carry a disproportionate burden of glaucoma and glaucoma-related blindness. Not unexpectedly, our participants who underwent glaucoma surgery were higher proportion at our academic center. It's a tertiary referral center for glaucoma and a well-known center. And so we were not surprised by that in the general, sort of population-based cohort that this was not as high. And so you can see that, when we did models trained with our All of Us data set, we achieved, pretty good predictive performance here. And one of the reviewers who reviewed our work said, well, is it just because you have a lot more predictor variables? What if you limit it to the same variables that you had in the original single center model? So we did that and still retained good performance. And you can see, I apologize, the scale of the ROC curves here are different between the two sides because we had done these in different environments. But our single center model, we kind of had performance hovering in the 0.7 range for the models. And with All of Us, we really achieved much better performance when we were using this large nationwide data set. So our key findings were that All of Us offered a larger number of participants, really a nationwide scale, greater diversity, particularly in better representation of women and Black individuals, and that it did perform better than our single center models. As we had hypothesized, measurements related to blood pressure and heart rate were important when we looked at sort of feature importance analyses. And, in summary, I think there's a lot of strengths to the All of Us database for ophthalmic research. They include, wide range of data types, nationwide scope, this emphasis on underrepresented populations. But, some of the limitations are that there's no imaging, there's no ophthalmic ancillary testing like fields. Right now, the ophthalmic observations are quite sparse. And of course, you still need technical and programming expertise to do the analyses. It's not sort of an auto ML platform quite yet. So just in the interest of time, I'll move ahead here. Here's our QR code for the paper if you're interested in learning more. And then our group has gone on to do several different research studies using the All of Us database for different eye conditions, including diabetic retinopathy, retinal vein occlusion. And so there's a lot of range of questions that you can ask with this database. And if you're interested in joining our OMOP work group to try to improve the ophthalmic data representation in All of Us, I encourage you to join that. We have monthly work group calls, and it's an open group, and everyone is welcome to join and contribute to that effort. Thanks so much.
Thank you, Sally, for this wonderful talk and for highlighting the wonderful data set that you're working with. Hopefully, there'll be more people using it over time. Our last talk of the day here will be from Darius Moshfeghi from Stanford, looking at an ROP severity score using photographs for decision making. Darius.
Thank you, Ted. It's been a great session. And these are my financial disclosures. I have a lot of conflicts in this space. Key takeaways. ICROP 1 through 3 created the framework for discussion of ROP location, severity burden, and treatment response. And all clinical studies to date have relied on this terminology at some level to stratify groups and quantify disease. The two features, plus and zone, have outsized risk burdens regarding intervention and outcomes. And the core features, zone, stage, and plus, can be used to create a simple photographic ROP severity score for ROP acute phase screening. The screening principles have been well elucidated for almost 55 years by Wilson and Junger, mainly meaningful target accepted treatment. And the granddaddy of screening, obviously, is diabetes screening and 7-field standardized fundus photograph. And as they've gone over all day long, the diabetic retinopathy severity score from 10 to 90 lets us know if the disease is getting better or worse. But from my perspective, the true genius of the DRSS is the conversion rate, taking these disparate features and allowing interconversion to a similar score, which allows you to go up and down on the scale. And we all know the metric of the 4 quadrants of hemorrhage and microaneurysms is equivalent to 2 quadrants of venous beating, which is also equivalent to 1 quadrant of intraretinal microaneurysms. And it's that allows you to take these different features and come up with a score, and then assess whether or not the diabetes retinopathy is getting better or worse on the scale of 10 to 90. You can follow it over time. Based on this, we've seen numerous AI approvals, both in the United States and in Europe over the last 8 years. In ROP for AI, Pete has gone over this extensively earlier and did a great job and has been instrumental in this. ROP meets the 10 criteria put forth by Wilson and Myung, although it's expensive, requires a lot of manpower to go out there and do this. We have a similar but more limited feature set, mainly zone, stage, and plus, compared to all of the features that they're grading in diabetes or retinopathy. And importantly, we have standardized photographs, which are very important for assessing and then training on, obviously. There have been three relatively distinct approaches for AI in this space. One is predictive using the WinROP, the ROP score, and the CHOP score. The other one is feature-based, looking at the vascular severity score, which we'll talk about in a second. And then finally, the one which is trying to bring them all together, which is the ROP activity score using zone, stage, and plus, the three main features. Predictive scoring does what humans can. It can obviously do the human based interpretation of the images, but then it takes all the demographic data, weight gain data, growth factor data, whatever that system is using, puts them into the hopper and ends up with this magical prediction that usually kind of says you're likely to develop ROP or you're not likely to develop ROP. And if you do, it's either going to be mild or severe. This is just one of dozens of papers. This one came out yesterday, and it's very important. The trouble with predictive algorithms is their pathway through the regulatory side is murky at best for screening in the real world. And then the second problem is that they represent huge liability in the United States. You have to be 100% correct. Otherwise, you have a blind baby and you're looking at a mid-8 figures lawsuit, which will settle out. The ROP vascular severity score looks at a 9-point level, but basically it's ternary. You either have no plus, you have pre-plus, or you have plus on this 9-point scale. And it looks why on plus, why are they focusing on that? That's what drives treatment interventions in ROP. This has been extensively validated both against expert ROP graders, both for disease spontaneous improvement or going on to requiring treatment, following treatment response, whether it's retinopathy or pharmacologic. And the regulatory pathway is they receive breakthrough status, and it remains to be determined whether they're going to go for a physician-assisted or an autonomous device. And we wish them very well because it's useful. Are the vascular severity score and the DRS similar? On many levels they are, in that you're looking at features, you're giving it a score, they've been validated. However, they're not completely analogous because some of the stuff that the vascular severity score does is more on the predictive side, using knowledge about what's going on in the rest of the eye from data that's been collected elsewhere to result in prediction of how much stage is present and what severity of stage is present. So an expert can't really come up with the same score for the totality of the prediction that the VSS can. The ROP activity score takes a bundled approach to this. It likes to say, hey, we want to look at zone and stage and plus and assign them these 23 levels ranging from 0 to 22 and come up with a score. And you cannot unbundle this. It's a little kludgy, and it has one big problem, which is that if you hold the zone constant, plus disease ranges from 2 to 19 points. And similarly for stage 1, 2, and 3, they have varying variations in their point level, which is intuitively kind of disconcerting. I always want to say, hey, plus is worth this, stage 1 is worth that, stage 2 is worth this. And here you can't do that. And there's no way, very similar to our CPT codes, there's no CCI edits where you can go in and unbundle it, which kind of makes it impractical for screening, and its lack of inclusion of ICROP terminology such as pre-plus, regression, and posterior zone 2 makes it also kind of impractical for interpretation. So based on this, since I do a ton of telemedicine just the old-fashioned way reading this, I was coming up with a photographic retinopathy prematurity severity score, and I wanted to base it on diabetes DRSS, but there's two key differences between diabetes and ROP. One, ROP moves really quickly, days to weeks, and diabetes is slow. And the second thing is that for all of its different features in diabetes, almost all of them are binary. They're graded on whether they're present or absent. And severity is basically counted by geographic location, as opposed to if you look at stage or plus, it can range in severity. Stage 1, 2, 3, 4, 5. Plus can go from none to pre-plus to plus. So those are the key differences. I wanted to have the interconvertibility. I wanted to weight the features that matter. Zone 1 matters, plus disease matters. So we gave them higher points. And then we wanted to use the existing ICROP terminology, maintain constant values, make it reproducible, simple, and of course, the ability to adapt over time. We came up looking at the 6 treatments. We assigned a score of 55 for treatment, which for the ROP activity score is 13. And everything less than that would be a monitoring zone. We looked at this retrospectively in the ROP Sundrop database, and we saw that we were able to score 100% of both eyes, whereas ROP activity score can only do about 81% and only identified 70% of treatable eyes. And their limitation was the unscorable ones were posterior zone 2, which they can't handle, regression, which it can't handle, and then of course pre-plus, which it can't handle. We have a prospective subgroup analysis of the scoring coming from the long ROP study, which was 12 pediatric retina specialists, 240 examinations, 480 eyes, and we're in the process of evaluating that currently. Why is this interesting and important? The NICUs are out there. They're widely distributed. They're each doing screening different from each other. And when we give them zone, stage, and plus, they really don't know how to interpret it. We have to make it easy for them, particularly since only 55% are adhering to the joint statement screening criteria for gestational age inclusion, and only 72% are adhering on birth weight criteria. And they believe they're doing a great job in including every baby that needs to be screened, when the reality shows that up to 16% of eligible infants aren't being screened. We have to make it simpler for them, one score that they can interpret. So at the end of the day, the key takeaways from the ROP photography severity score is that zone, stage, and plus can be used to create a simple score. Validation is pending our analysis of the data, and much work needs to be done to ensure eligible babies are being screened and then scored before we can even think about deploying AIs in these populations. Thank you for your time.
Thank you, Darius, for that really interesting talk about simplifying the ROP screening methodology for the world. We're going to move to our panel discussion here. If all the speakers could please unmute themselves, and we'll start with a question. See, for Sally. I think the work you're doing with the this data set with the All of Us EHR data set is amazing. Have you found that your findings have aligned with or differed from those people who are using the more traditional visual field and imaging data to train glaucoma machine learning models?
I don't think this replaces those models, but it just gives us another avenue to investigate. In fact, we have a computational ophthalmology group at UC San Diego, where we are working on multimodal deep learning models that will incorporate the imaging metrics alongside the systemic data from the EHR. So my hypothesis is that putting all that information together is going to be better than either one alone. The one advantage I think that we do have when looking at EHR data is trying to build in like real-time clinical decision support. A lot of that infrastructure already exists. Epic has sort of decision support. Epic is our EHR vendor, and I'm sure people have other vendors that they use, but many times, those structured data elements in the EHR systems can easily be called and then fed through an engine or a model and then provide some sort of risk stratification for the physician at the point of care. Obviously, integrating imaging and fields is a little bit trickier because it involves communication with PAC systems. And as we know, for ophthalmology, there's a lot of issues with DICOM adoption and sort of interoperability between EHRs and PACs. So I do think having the EHR data provides one avenue for perhaps an easier pathway for AI integration into clinical practice. And that's another thing we're working on at UC San Diego with our innovation center at the health system. But, you know, I think that we were actually surprised by how well these models predicted glaucoma progression in the absence of the eye data that we traditionally look to. But in my mind, the best performance will come when we're able to combine those different modalities.
Thank you. For Daniel, when you did the disease classification, did you use a two-dimensional B scan or did you use 3D volumetric analysis?
Okay, no, it was by analyzing two-dimensional scans. Yes, it was. I think that for the next projects or researches with 3D scans.
Great. And then, you know, what do you think are the next steps on moving this fluid detection algorithm forward and getting it really, you know, operationalized in the clinics that we're using?
Yes, we want to incorporate some new elements, including, for example, demographic information that could be especially useful in order to analyze them for more application and not only for the screening of these diseases. And that's why we are moving on from other ophthalmology centers and readers in order to make this more applicable to other populations.
Thank you so much. A question for Fatala. We had in our last session a presenter from Wisconsin that was also looking at 7-field fundus photos and the necessity for maybe using wider field imaging to detect abnormalities outside the traditional 2 fields that are being used by the FDA cleared algorithms. You know, how would you say your algorithm would add to the performance of the IDXDR and the iNOOC algorithms?
Well, first of all, the IDXDR and iNOOC algorithms have been tailored to detect more than mild diabetic retinopathy. And were our algorithms or the one which had been presented by the Wisconsin Reading Center was tailored to detect a different disease scale, which is specific and above more than mild. So that's number one. Now, when it comes to the input image data, the need for having wider field view is clearly needed because the disease classification is indeed based on 7 fields and covering wider field of view. So we performed actually similar simulations as the ones which were reported by the Wisconsin Reading Center by restricting at this time image data to the model, restricting only to the central fields of view. And we observed an additional drop of performance, not dramatic. And actually it was similar to what had been presented earlier, that as the cases which ended up to be false negatives were mostly cases where the lesions were not visible on the central field. So at the end, the algorithm sees what data is available to it, and the wider, the more it would cover in terms of the retina, the disease pathology, the better for the model's performance.
Thank you for that answer. For Yasha, you know, I think the potential for AI to help us make medical decision making at the point of care, I think, is one goal I think a lot of us have in the clinical realm. And your study kind of gave us a picture as to how that might happen. You know, what do you think? You know, given the limitations, you know, the small sample size and the validation, what do you think the next steps are into actually allowing models, you know, to help us decide what treatment to give and when to give it in the clinic?
Well, I think, first of all, there's a number of non-machine learning based approaches to this where we're actually inputting, various biomarkers and then looking at predictive values. There's a greater granularity to that. And the idea of machine learning is that perhaps it will provide you some identification of features that maybe we didn't think about in the more traditional fashion, like looking for drill or easy loss. And the interesting thing is what's sort of come up even in small data sets relative to some of the work that we've done with the SCORE2 group is that visual acuity still remains one of the most strong prognostic factors in terms of ultimately predicting final visual acuity, and also helping you to understand the need for treatment frequency. So, I think we need to have some level of granularity if we're going to be using both sort of more traditional machine learning approaches that really look at some of the biomarkers, looking at maybe some systemic features to help us better predict this. I think we're still very much in the exploratory phase, and we've got a long ways to go before this can be implemented clinically.
Thank you. Darius, you went into your talk about creating this simplified scoring system for ROP, and as clinicians, we always like the mantra of keep it simple. What do you think the next steps are going to be in implementing an ROP system like this in the United States?
Thanks, Ted. Yeah, we have a real knowledge gap between the NICU physicians and the nursing side, as well as the telemedicine side. And I mean, it's just so emblematic when you look at them. We've had this joint statement screening guidelines going back, 30 years, and we can't even agree amongst, neighboring NICUs on what the criteria will be for birth weight inclusion or gestational age inclusion, on when to screen the babies. They're all doing it differently. So imagine then I'm giving them zone, stage, and plus, and telling them, oh, the baby's getting better or worse. They don't know what to do with that number. And so, with that information, they got to look it up. And I figured that if we had one score of some level, and they could go and say, oh, it's better or worse, or it's pass or a fail, at least the NICUs that I'm doing telemedicine in can then understand, oh, well, 55 is bad, it says treat, and everything less is, they can monitor and are, they're managing 10 different subspecialists. The retina pediatric ophthalmology people are just one. And, they wanted to keep their little checklist also very clean and uncluttered, and be able to communicate effectively both with their healthcare teams and the families, and also stay on top of me. They can follow the score. And if I say, follow the baby in 2 weeks, and they say, hey, the score is worsening, why are you doing that? We can have a conversation about it.
Wonderful. Alvin, I really enjoyed your talk about the real world implementation of AI and DR screening. We heard a talk in the last session from David Myung about their implementation on the West Coast, and probably some differences were due to the different demographics of the screening population. One of the big discussion points, I think, between ophthalmologists who are looking at images and making diagnostic decisions and the primary care clinics where the screening is being done is the issue of dilation. So you did touch upon that a little bit, but did you find that there was much resistance from your partners in primary care for dilation? And how did they work around issues for workflow to build in dilation time, for example?
I think overall speaking, what I realized, not surprisingly, is that in projects like that, it's good to get the other side involved early on from the beginning, and try to line up the incentives of both teams as much as possible. From my point of view, if I have my way, I would dilate every single patient to really just maximize the diagnostic rate, but that is not practical or desirable from their point of view. So I think the key is try to come up with a compromise where the diagnostic rate goes up, from my point of view, but also something that makes it easy for the workflow. And I think that's the kind of conversation. It's really location specific. even within Hopkins, there's quite a bit of variability between the 4 sites in terms of the amount of manpower available and the desire of the leadership at each clinic in terms of making this a successful project. So that's my long way of saying, I think the devil is in the details. It's really a human interaction thing. It all depends on the specific clinics that are doing it and trying to understand what the pain points are. Because even within Hopkins, some clinic are more willing to do dilation simply because they have 2 additional medical assistants, as simple as that. So it's all in the details.
Thank you. Well, we'll have time for one last question, and this is going to be for Aidan. I think it's really interesting you brought up the use of different fluid analysis and how that could diagnose eye disease. Do you think that that this is a feasible and scalable diagnostic technique, and do you think it might replace imaging-based diagnostic AI tools in the future?
Yeah, that's a great question. So, I should say right now that biofluid-based AI diagnostics are much earlier in development than imaging-based ones. And so right now, a lot of the reports about imaging-based glaucoma diagnostics using AI, they're much more accurate. Like they have accuracies of 98%, rivaling or better than specialty trained ophthalmologists. So right now, probably not. And it is also true that, images will always be less invasive than any type of biofluid collection. Even if it's just like serum or anything like that. So probably not replace, but could definitely augment. But where I really see the strength of these biofluid analysis using AI is sort of pathogenic exploration, like development of sort of personalized glaucoma management strategies and new therapeutic sort of options.
Well, thank you so much. This brings the discussion portion of this session to a close. Just want to thank all of you again for these wonderful presentations and participating in the Q&A process. And I also just want to wrap up the entire meeting here on behalf of my co-directors, Rishi Singh and Jenny Lim, that this has been a huge success, our 2nd year now. We all look forward to seeing you again next year. I also want to thank iVista Medical Education Avenue Live for the support for putting on this meeting, and we look forward to seeing you again in the next time we do this. Have a great rest of your weekend.